Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Especially on this particular day, because this is going to be a long one, folks. Not just for this video, but just my self-recording for this day. At least the plan is for such. The video you're watching right now is going to be regarding Integrated Math 2. Things where you would do probably at the second semester of an Algebra 1 course with quadratics. Not very many things there. I'm actually not covering exponential functions in this or geometric sequences or anything of that ilk. And then a lot of second semester is geometry stuff where you do things with parallel lines and triangle similarity. A lot of things regarding parallel lines and similarity, actually. That's the big part. And then circles. We finished on circles and doing things with tangent lines and secant lines and things of that sort. There are certain problems that aren't hit in this video as well. But this is an overview of our semester. This is my students' final exam review. And this is a big packet, and there are so many problems that I didn't even assign them all the problems in there, specifically because they're triangle congruence questions. The one I'm looking at right now, actually, I believe, is regarding triangle congruence proof. I'll still do it for those who are watching it, for those who may have to do it, and maybe for my students who are interested in things like that, but they're not required to do that. Now, the thing I'm going to provide for you here, and I promise to do so, I can't guarantee if when I publish it they'll be there, but I do plan on providing you not only timestamps in the description section down below, but also PDFs of the material, and also because these are mixed review. I'll preview it all beforehand. Mixed review of everything, and they come in such a different smattering of events that you're going to see some things and you'll circle back to them later, and they can be out of order. Because of that, I'll perhaps try and section them off and say, here's where you can find these kinds of problems, here's where you can find these kinds of problems, etc. But if you have the packet for yourself, then you'll know exactly where they are. Now, like I said, this is a lot of stuff here. When we look at this, and I'm going to kind of zoom out right now and kind of show you the zoom out version of this. So here's the first page, and it is just proofs literally right there. But here's the first page. By the way, when you look at these will be 6 different reviews. You might see this say review for second semester final part 1. Every set, I believe, consists of 3 pages. So here's page 1, 2, and 3 of part 1, and then page 4 is, and I don't have the pages on the bottom, but if you number the pages, that might help. I'll try and say them out loud or something. But page 4 is, oh, I guess this should say part 2. But anyway, final review, part 2 right there, 4, 5, 6, page 7, part 3, page 12, or whatever, page 10, part 4, you know, it keeps going. There's 6 parts. Looks like this has multiple. Here we go, part 5 and part 6. 6 parts, 3 pages each. That is 18 pages worth of content. I don't know how many problems it specifically is, partly because some of the numbers reset. Most of the time it tends to be when you start to do a different review. So I guess as a part of everything, I will also consider what page numbers I go into for all of them for you as well. Lots of problems. It might be over 100, whatever it is. And as I'm taking up time right now, I'm in my 3rd minute just talking to you right now. I want you to keep some things in mind. I want you to think of this kind of like Fight Club. Besides, you can talk about it. But this video will go on as long as it has to. So it could be a few hours. I'm not sure yet. And at the point of recording, you already know how long it is because you can just look at your time slider. But also, if I go limp or tap out, the video's over. It's kind of a Fight Club rule. Not necessarily, but you know, I actually haven't recorded a video in a couple weeks. I've actually been dealing with a back injury, and I still kind of have it in such a way that actually it's sitting that makes it worse. So I've waited long enough. I wanted to do this last weekend, but I've been waiting long enough to try and get it to heal to the point. By the way, I'm going to have to get a water bottle pretty soon. But there are points I'm probably going to have to pause this video for whatever personal reasons regarding back, regarding water. I take a phone call, whatever it is. I may have to have pauses at some times during the video. And let this be a precursor for the other videos I have to do, because not only am I doing a final review for Integrated Math 2, but I'm also going to be doing them for Integrated Math 3 and 1. I don't know if I think that's the order I'm going to end up doing them because of the time frame that I need them to get done by because of when they're taking their finals. So that might happen today on this particular Saturday here, where you get to enjoy, I think, some softball, I think it is in the background, or hockey, whatever. I don't know what's happening now. Without further ado, guys, I am going to get started, but keeping all that in mind when I said it goes on as long as it has to, I'm not going to spend a long time talking about things that I've taught before in the past, so it is up to you to explore the rest of my YouTube channel to find the certain content that you want to hear, or if you're one of my students, to have the notes and access to them, or just go with it. because I can't reteach everything, but I am going to redo everything. So if I end up going along speedily, I'm just going to do that. And there are times where I will show you my calculator, right? There are times where I'll go to the calculator right here, but there are times where I will just use my own right here, just because I have to click around to make the buttons happen here, but I'll show you maybe once how it works, and then we'll go from there. All right, let's go ahead, guys. Let's go ahead and let's get started on this. Hold on. Where's my... There it is. Let's go ahead and let's get started on this right now. This one, the proofs don't actually even have numbers to them. And like I said, this thing may be way out of order from what we're doing. I didn't even do these with my students here. But here we go. Given XYRS is a rectangle, we want to prove that segment XM, and given segment XM is congruent to segment SM, we want to prove that M is the midpoint of YR. So part of the things with proofs, and I don't know if it's 7 steps long, I don't know, I'm going to do this on my own for the first time. Part of the things with proofs is you need to know your end goal, and I sometimes tell my students, think of it like a maze. You want to try and maybe say, how are you getting to that end? Maybe even work backwards through the end. For example, if you're going to prove M's the midpoint of YR, you're going to have to somehow prove that MR is congruent to MY. And in order to do that, you probably need to prove 2 triangles are congruent. So given the givens that they give us, given this portion right here, I want to mark those two, that those two are congruent. I'm already going to write that. I'll write it in the second step because we already have the first step going. What I'm pointing out, though, is the very fact that we're probably going to look here and prove this triangle is congruent to this triangle or something of that nature. I still don't actually... I'm still actually now thinking about what it is. Oh yeah, you know what? Yeah, I can do that. I'm going to prove those 2 triangles are congruent to each other. So I want to prove this triangle is congruent to this one, and then by what's called CPCTC, show that the corresponding parts here and here are congruent. Therefore, it's a midpoint. So here we go. Let's go back to the fact that XYRS is a rectangle. Let's write that out. XYRS is a rectangle. And that is also given. All right. How can we use the fact that it's a rectangle to come up with some other stuff here? We have this given right here. Well, what does a rectangle have? It has opposite sides congruent, and it has all right angles. Now, I don't know if I want to mark all of that up, but I do want to mark up the things that do have to do with it being a rectangle with respect to this triangle here. I can make this right angle here and this right angle here. I can say angle Y and R are right angles. Are right angles. That's a definition of rectangle, right? Based on it being a rectangle. By the way, I might write some things very shorthand. I might write def like I did RT angles like that. If Y and R are right angles, there's kind of one of 2 ways you can do this. I don't have to necessarily state that they're congruent. What I would either have to do is state that they're congruent or state that these exist as right triangles, because the proof that I'm going to do for this, I'll skip statement 4 for a moment to state that I want to show that these 2 parts are congruent by definition of a rectangle as well. Opposite sides are congruent. And I'm going to prove these triangles are congruent using what's called HL, hypotenuse leg. Hypotenuse leg only exists in right triangles. So the fact that these are right angles makes me want to state here, oh, hang on, XY is congruent to SR by, you know what? Can I do this if you don't mind? Let me just put this as a part of this statement right here. Just part of statement 3. So boom, boom, by definition of rectangle. So both of those together, because otherwise I think I'm going to run out of step room. Who knows how many steps this is supposed to have, you know, really. They gave me 7, but I think I've done proofs that were less than 7 in here. Just to change the color coding here. Triangle XYM and triangle... Let's see, XYM and SRM are right triangles because the definition of a right triangle, it's a right triangle that needs a right angle. Each of these have right angles here based on the previous statement. Now, something I like to do is draw arrows leading into other statements. This statement here led to these 2 statements here. Remember, it is technically 2 statements here. And then this right angle statement led me to the right triangle statement here. Now, we did also say that XY was congruent to SR. That is a part of statement 3. And because of these being right triangles, because of XY being congruent to SR, and because of XM being congruent to SM, these 2 triangles are congruent. Triangle XYM I'm on the first problem still, this whole thing. Is congruence triangle SRM, because it's a proof, is congruence triangle SRM by, oh, I'm sorry, you probably can't see because the picture here. I got to be conscious of that. By HL. It's the HL triangle congruence theorem. I'll just put HL congruence there. Hypotenuse leg. The hypotenuses of these two right triangles are congruent to each other. One set of legs are congruent to each other. This is not a side angle side case. That would have been if these two were congruent, which, by the way, we're going to make that statement next. That does mean that MY is congruent to MR right here because these are corresponding parts of congruent triangles. And I also, in this triangle statement, I didn't mention this here, but in your triangle statement, you want these parts to also correspond here. X should correspond with S, Y with R, and M with M. X corresponds with S, X, Y, M, S, R, M. R corresponds with Y, M corresponds with M. So now in that letter order, you can see where I wrote MY, the third and second letter, MR, the third and second letter. They correspond with each other. The statement CPCTC stands for corresponding parts of congruent triangles are congruent. If the triangles are congruent, then the corresponding parts are congruent. And you know what? If you have two congruent collinear segments, such as these ones right here, then that must mean that M is the midpoint in that scenario right there. So if M is the midpoint of YR, that's because it's the definition of midpoint. So the last statement is the proving statement. And I just saw a text on my computer screen regarding a student who wants me to tutor them this weekend. Not tonight. I'm not tutoring tonight. I'll have to respond to them in a few hours here, or if I pause. What is this? Definition of midpoint. Okay, so there is one problem down, and we are 12 minutes in, and we have probably 100 to go or more. I have no idea. But like I said, that was a proof. That was a lot longer than others, and this is another proof. I think there's several proofs here. All right, segment AB is congruent to segment AC. That is given. This is one of those things where I already made a statement there. I already did a problem with a proof, and then I'm just going to go ahead and move on and start the next one. Segment AD bisects segment BC. Now, I will write this for now. Why don't I just write it up here? AD bisects BC, another given. What I tend to do here is I want to make my own statement automatically right now and just say, like, okay, well, that means that I want to mark these. If it bisects the segment, then it divides it into two congruent parts. And by making that statement, by marking that up, I can make that statement. Segment BD is congruent to segment CD. And I want to kind of correspond parts there. That's the definition of a segment bisector. That's because of that previous statement. Segment bisector. Now, I don't know if I can make this statement fair and right off the... Oh, you know what? Never mind. I know what I'm going to do. I was going to say that I don't know if they want me to... If I'm allowed to say the triangle's isosceles, therefore these angles are congruent, which you could do, but that's to prove the triangles are isosceles. I think this is part of the triangle isosceles proof-ish thing. But what I'm going to do is state that this segment is congruent to itself. DA is congruent to DA here by what's called the reflexive property. It's a statement that says that a shared part in two different objects are congruent to itself. It's called the reflexive property of congruence. Reflexive prop of congruence. Now, there is a triangle congruence theorem called side, side, side right here. Side, 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 and side, side, side. That lets me say ABD and ACD are congruent as triangles. Triangle ABD is congruent to triangle ACD. And if you're still in the dark regarding what I'm saying there, what I'm saying is that there's only a minimum amount of information that you need to prove triangles are congruent. If you know all three sides in two different triangles are congruent, then that's enough. If you know two sides and the angle in between is congruent, then that's enough. If you know two angles and the side in between of two triangles is congruent, that's enough. Two angles and a side outside of it are congruent, or in a right triangle if the hypotenuse and leg are congruent. Ones that don't work is you can't do angle, side, side, and yes, I did write ass. You can't do angle, 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 or angle, angle. Those aren't ones. I should probably mark that in red. Those are common ones that people want to try and run into, and there are no two-part ones. HL is not a two-part one because there's the right angles that are congruent as well. But there are no two-parters, just three minimum, and this is what we need here. If the triangles are therefore congruent, that does make angle 1 congruent to angle 2 by CPCTC. The triangles are congruent, these corresponding parts are congruent, and they do correspond. This is angle BAD, it's 213. This is angle CAD, 213. So angle BAD, angle 1, I'll just call it angle 1. I almost want to call it BAD and C. Angle 1 is congruent to angle 2 by CPCTC. See, we didn't use 7 steps there. I actually technically probably used 6. All right, let's not do proofs, hopefully. Yay, here we go. Okay, simplify these show all work. Now, simplifying means that you, in these cases here, if there is a negative inside of a square root, that shouldn't ultimately be the case. We would love to pull out instead an I in that instance. I is an imaginary component for numbers that multiplies with a real number. I represents the square root of -1. And the other part of simplifying that will be needed for the first problem and for the majority of these right here is that you need to pull out any perfect square factors that exist inside your values, such as a 4, which is 2 squared, a 9, which is 3 squared, a 16, which is 4 squared, and the list goes on. If these numbers are the number itself that's inside the square root, or if they exist as a factor inside your perfect square set, then you'd want to factor them out. And it's preferred to find the largest perfect square factor possible. I'm going to go up to 15 squared. I doubt I need all that. But that's up to 15 squared right there. The point is, here's a perfect square factor list, and you want to find the largest possible. And this is one of those cases where I could say, or you could do it this way, or you could do it this way, or you could do it this way. I'm going to try and cope with what I feel is the best and most efficient way possible. And trust me, I'll end up going faster later if we run into more like these or something of that ilk. Square root of -24 is also I times the square root of 24. Automatically, you probably want to pull out that I in knowing that that will occur there. This is actually not a negative number. In fact, it's an imaginary number. And as I've said before, imaginary numbers don't mean that they're made up. They are just as real numbers. It is just the semantics. Okay, the square root of 24 can be broken up into the square root of 4 times the square root of 6. I chose 4 because I can take its square root. The square root of 4 is 2. I times 2 can better be written as 2i. This is 2i root 6. That is a simplified version of that problem there. Let's change these to black up top so I can change colors down below. All right, number 2. The square root of -242. Again, also, I tried to change my color. Also, you can call I root 242. I think here on out, I will probably pull out the I on its own in some different whatever way. 242, you could factor out not a 4. You can factor out a 121. I can say that because this is half. 121 is half of that. 121 in root 2. Square root of 121 is 11. That becomes 11i root 2. Again, pull out the largest perfect square factor you can so you avoid having to repeat these over again. Now, this is 3i times the square root of 2 times the square root of -12. Let's work on simplifying this guy first, maybe just on the side, little side project, and then let's multiply it by the 3i root 2. Let's see what's going on. Well, 12 is, let's see if we can do some of this in our head. Root 12 can be rewritten as root 4 times root 3. Square root of 4 is 2, so that becomes 2 root 3. So the square root of 12 is 2 root 3. Square root of -12 should be 2i root 3. So this would become 2i root 3, right there on the side. So we have 3i root 2 times 2i root 3. Now make no mistake, everything here that you see is being multiplied. Maybe you don't write it like this. If you're uncertain what to do here, separate it. 3 times I times root 2 times 2 times I times root 3. Literally everything here is being multiplied. And the best way to multiply these are things that are, I'm not going to say like terms, but things that multiply with each other. 3 multiplies with 2 to get 6. I multiplies with I to get I squared. We'll talk about that in a second. And root 2 times root 3 can multiply to become root 6. Now the things that you look to clean up. If I represents the square root of -1, then you square both sides right here. I squared equals -1. And that's very true. I squared is -1. That becomes 6 times -1, which is -6. -6. And if you could simplify the square root of 6, you would do it. I cannot. There is nothing else to be simplified there. There are no more perfect square factors that exist. I am done. Okay, number 4. The square root of 18 times x to the 4th times y to the 7th. You can kind of treat these as little separate bits here if need be, like root 18, root x to the 4th, root y to the 7th, like so. Root 18, root 9, root 2, 3 root 2. So there's 3 root 2. When you simplify root x to the 4th here, you have to keep in mind that, so there's a property. If you take a square root of something, then that's also raising to the 1/2 power. And if I raise x to the 4th to the 1/2 power, that's like multiplying the 4 with the 1/2, which means it's like dividing 4 by 2. When you take the square root of something, you divide the exponent by 2. So I'm going to divide 4 by 2, and ultimately it becomes x squared. The square root of x to the 4th is x squared, because if you square x squared, you get x to the 4th. You can do the same thing with this one right here. The difference is that 7 cannot divide by 2 evenly. You don't get an integer out from it. So maybe a rewrite for this that you would want to consider is split up y to the 7th into root y to the 6th times root y. You know, there are some things like this root 2 that just cannot come out of a square root. Y to the 6th is a perfect square. I can divide 6 by 2. I can't divide 1 by 2 evenly. So I will leave the root y inside the radical. But I can do y to the square root of y to the 6th. 6 divided by 2 is 3, and that becomes y cubed. And we're still left with a root y. Sometimes there are just things that are still perfect squares there. So whatever remains is there. Multiply everything in front that's rational. Keep everything inside a radical that's irrational. 3 times x squared times y cubed. 3x squared y cubed is outside the radical. Inside the radical is 2y. 3x squared y cubed root 2y. Number 5, we have 7 minus 3i times 4 plus 5i. This is foiling, guys. Distribution. First outside, inside, last. Multiply these, see what comes out. 7 times 4 is 28. 7 times 5i is 35i. You add these. Negative 3i times 4 is negative 12i. You add it. Why did I subtract? Because I added a negative. Negative 3i times 5i is negative 15i squared. Remember, you are multiplying a negative. Remember, you are multiplying your i's there. Combine like terms. This is going to come in what's called a plus bi form. When I say a plus bi form, I mean that there's a possible real term and a possible imaginary term. We're going to make sure to have both. The I squared, if you recall, is a negative 1. So while I combine 35i with 12i to get 23i, I will have negative 15i squared becomes negative 15 times negative 1, which is plus 15. And that should add with the real number 28 to then get 43. So I would be left with 43 plus 23i. Okay, number 6. As far as simplifying here, there are kind of two portions that we need to take care of. The top here is simplifying that upper radical, the square root of 48. Now you can divide a 16 out of the 48 right there. So root 16 times root 3 becomes 4 root 3, like that. And you'd be with 4 root 3 over 3i. And you think you'd be done. Now, here's what you can't do. You cannot divide the root 3 by 3 and like cancel them out and do something like that. Nothing ridiculous like that, guys. If these could reduce, go ahead and do it, but we can't. However, you cannot have an I in the denominator. You cannot have a square root in the denominator. Your denominator should be void of decimals, negatives, fractions. True of numerators as well for fractions and decimals. But it can't have an I. You have to have a whole number integer in your denominator. So how do you get rid of that I? You don't just wipe it out. You have to do something to it so that it is gone in the denominator, even if it means it comes up in the numerator. If I multiply the top and bottom here by I divided by I is 1. So I'm not changing my value. But I am rationalizing the denominator. I'm turning it from an imaginary number to a real number. Why is that? Because the bottom becomes 3i squared. Well, 3i squared, and the top is 4i root 3, by the way. I squared is negative 1. That becomes negative 3. Or I could put the negative right out front right here, and I get negative 4i root 3 over 3. The answer is still imaginary, and it's still irrational. I haven't changed anything there, and I couldn't. It's still an imaginary number, but the bottom is now an integer. In fact, a positive. It's a whole number there. So I have now... It might not look simpler to this than you, but it is simplified, and it is fully simplified, and that is the answer that is being sought. Okay, number 7, 8, and 9, solve and show all work. These are quadratic equations, and they, by and large, in this situation, may have complex solutions, meaning things with a plus or minus bi kind of form right here. They may not be factorable, and this one doesn't look as such. But what I do have here is I have an x squared term. I have no x term. So probably the most preferred way to do a problem like this is to get the x squared by itself. Let's subtract 14 from both sides like this. Now let's get the x squared itself by dividing both sides by 3. I square a number and I get -2. How is that possible? I thought squaring numbers led you to a positive result. Well, if the number's imaginary, take the square root of both sides, see what you get here. You get technically the absolute value of x on this side, but I'll just call it x, knowing that we're supposed to put a plus or minus over here. So x is plus or minus. What's the square root of -2? Well, that's I root 2. We go back to simplifying that. And those are your answers. X is positive I root 2. X is negative I root 2. Whether you put one or those into the value for x there, you should get a true statement out. And that's all I'm going to say on that. Number 8. X squared minus 2x plus 12 equals 3. Now, I don't know if I'll do this for every problem here, but I will start at least on this one. You have two different options for which you can solve. One way is attempting to maybe factor. You go ahead and you subtract the 3 from both sides. You set this equal to 0. And you say, well, are there two numbers that multiply to make 9 and add to make -2? You find out that's not the case. So you say, all right, my only two options left are quadratic formula, which I'll do first, or completing the square, the option I prefer. Quadratic formula I'm going to do because it's already in standard form set equal to 0 now. So you say, all right, quadratic formula is, I'll put QF. If you have a quadratic equation set in standard form set equal to 0, then x equals -b plus or minus the square root of b squared minus 4ac, all divided by 2a, where a is the quadratic coefficient, b is the linear coefficient, and c is the constant. This guy inside here is known as the discriminant. It's something that I like to evaluate first for several reasons, among them which we can know how many solutions there are, and it makes the workload a little bit cleaner because you're not spending time writing everything else in the problem when you're doing most of the work inside here. So for the discriminant, I'm going to evaluate b squared minus 4ac. That becomes 4 minus 36, which is -32. This is the thing that we will be taking the square root of in this problem here, the square root of -32. If you don't mind, I'll just keep cleaning that. Well, actually, no, I'll just do it in the problem itself so you know what we're doing here. So that's going to be x equals, here's -b, the opposite of -2, plus or minus the square root of b squared minus 4ac, all divided by 2a. Now the square opposite of -2 is 2. And the square root of -32, you can pull out a 16, right? Root 16 times root 2, so it becomes 4 root 2. So the square root of -32 is 4i root 2. So plus or minus 4i root 2, all divided by 2. Yes, I am expecting at this point that you either go back and figure out how I did that by saying it out loud, or you carry forward and accept and move on, because that's what we're going to go through, right? The video goes on as long as it has to. Now, both of these terms here can divide by 2. 4i root 2 and 2 can both divide by 2, in which case you actually just divide the 4 and the 2 by 2, and you get a 1, and a 2 here. So x equals 1 plus or minus 2i root 2. That is the final set of answers. Those are the final answers there. Now that was solving by quadratic formula. Now that is one approach, and I kind of took on the approach because, like I said before, I just put this in standard form. Maybe I felt it was worth it to do there. I prefer to solve this by completing the square in general, though. And I say that because completing the square, for me it's cleaner, but for me it's also best used as a practice when you already have a 1x squared. That's very important. And this term is a linear, it's a even linear coefficient right here. So what I'm going to do here is take this exact same thing from before, and I'll subtract 12 from both sides instead. X squared minus 2x, and I'll subtract 12 over to get -9. I'm going to add in a term here that is going to give me a perfect square trinomial. Again, I'm talking a little bit on this as if you've heard it before. What to do to make a perfect square trinomial is, provided you have a 1x squared here, you take the -2, the linear coefficient, divide it by 2. Literally, just by 2, not because this is a 2, but you actually take half of it. You take half of this number to get -1, and then you square that value. -1 squared is 1. So a 1 would also go over here because that's just balance of things. Like I subtracted 12 from both sides, I'm going to add 1 to both sides. And I do this because I've made what's called a perfect square trinomial, something that you can factor down like so. This is x minus 1 quantity squared. The two numbers that multiply to make 1 and add to make -2 are -1 and -1, that guy right there. and it makes this. Negative 9 plus 1 is negative 8. Why did I do this? Because now I can solve using square roots. I can take the square root of this side and this side, just like I solved right here. So let's keep going. The square root of x minus 1 squared is x minus 1, or absolute value of x minus 1, but I'm going to put a plus or minus there to seal the deal. The square root of negative 8 has an I in it. The square root of 4 times square root of 2 gives you 2 root 2, so this is 2i root 2. Add 1 to both sides, you get x equals 1 plus or minus 2i root 2. Am I covering that? I'm sorry, I sort of am. 2i root 2. Hey, that's the answer that we got here before, and they should match. If this was multiple choice in the final, that is the answer we're looking for. Probably nothing else, I'll be honest. So whether you use quadratic formula and you prefer that, knowing how you had to simplify this radical, how you had to simplify the fraction, know the quadratic formula and all that, or whether you do completing the square, is your call. Now we look at number 9, where I'm less inclined to solve by completing the square because this is not a 1x squared, and dividing by 2 would come at the cost of leaving us with fractions. So I'm likely going to not complete the square. Quadratic formula seems like the most likely candidate, unless this is possibly factorable. So if I subtract 3x and add 1 to both sides, I set it equal to 0. Quadratic formula uses standard form set equal to 0. Factoring starts off in a standard form set equal to 0. I'm going to test this. This is factorable. I'm going to test for factorableness here. I want to see if there's some 2x and x here. Positive product, negative sum leaves me to a minus and minus here. The only factors of 1 are 1 and 1, or negative 1 and negative 1. And we can see if by foiling this thing, this is 2x squared, plus negative 2x plus negative x. That's negative 3x, plus 1. That's the factorization. So why might you factor this way? Because zero product property is fun. If this times this equals 0, either this equals 0 or this equals 0. So either add 1 to both sides and then divide by 2, you get x equals 1/2, or add 1 to both sides, you get x equals 1. So there's one way to solve this by factoring, just because it was factorable. I will, however, use quadratic formula to solve because maybe you don't know the factorization. And I want to show you another version of quadratic formula. I just don't know how to write it. I guess I'll do it down here. Hope you don't mind. Here we go. 2x squared. Actually, I'm going to start on this stage here. 2x squared minus 3x plus 1 equals 0. Let's go ahead and use that quadratic formula. Start with the discriminant of b squared minus 4ac. b squared minus 4ac, which becomes 9 minus 8, which is 1. 1 is what goes inside the square root, right? The square root of b squared minus 4ac. And the square root of 1 is 1. So if you don't mind, I'm going to try and write this stuff a little bit faster here. We get x equals, you know what negative b is? Opposite of negative 3. That's 3. Plus or minus, the square root of b squared minus 4ac. The square root of 1 is 1. All divided by 2a. 2 times 2 is 4. 3 plus or minus 1 divided by 4. Do I leave it like that? No. Because you can actually combine like terms here, unlike if it's irrational and or imaginary. Here we can actually do 3 plus 1 and 3 minus 1. So x equals 3 plus 1 over 4, which is 4 over 4, which is 1. Or x equals 3 minus 1 over 4, which is 2 over 4, which is 1/2, this or that. Have we seen those answers before? Heck yeah, there they are right there. 1/2 or 1 or 1/2. We get the same answers. Quadratic formula or factoring, they're all one the same here. Okay, I need to get some water here. I'll be right back. Okay, and we are back. All right. I guess I can leave that stuff there. Okay, write an equation of each circle in standard form, then graph. So, as far as circle equations in standard form, it is x minus h quantity squared plus y minus k quantity squared equals r squared. Your center exists at h comma k. And the radius is at r. So what's interesting here is we're given the information, which is actually the best way to go to both write the equation and get the graph. See, if I ever wanted to graph based on an equation, I'd want to get the information first. If I had this, I'll say, what is my center and what's my radius? Okay, now I'll graph it. If I had the graph, I'll say, what's my center, what's my radius, and I'll use that information to make the equation. But I have this, so I'm in perfect prime position to do both right now. My center is at my hk. My h is -2, my k is 1. My radius, r, is 4. So as an equation, this is going to be x minus h minus -2 is plus 2 squared plus y minus k, y minus 1 quantity squared, equals r squared. 4 squared is 16. That's my equation. If I want to graph, forget the equation, just do the information. I'm going to start at negative 2 comma 1 right here. And then my radius is 4. So that means I should graph by plotting. See, the best way to count 4 for me, at least to complete my circle, is to just go up 4 from center, down 4 from center, left 4 from center, and right 4 from center, north, south, east, west. And then approximate the circle best as possible. Now, for you guys, you would generally just, I'd say go quarter circle at a time, like that, etc. For my time's sake, after this problem, you're going to see me use the circle tool. I'm just going to go ahead and expand it out. Let's see how close my circle is to an actual one. It looks like this one got a little dipped, but let's see. Let's get an actual circle here. Yep, looks like I dipped a little on the top right. Not too bad. But anyway, that's the idea of circle. I'll use the tool here on out just for time. Okay, so there's that one. Next one is going to be, well, this time we don't have the radius, and hopefully you can look past this information right here. The center is at negative 1, negative 2. That is my HK, but it contains the point 2, 2. I kind of feel like graphing first this time, and actually I kind of feel like moving my face over here this time as well. So here we go, and I got to probably do that more often when I can. The center's at negative 1, negative 2 right here. And it contains the point 2, 2 right here. Now, what they mean by contains the point is the circle is not the center. The circle is, the circle's not the center. The circle is this rim around it. And each part of this rim is a point itself. It's not just these 4 points that I came up with right here. It's everything around it. This is among them. Now, I can't count like this way and say how long that is, but I can count left, right, and up, down, just like we did for those other points. And I can use that information to go ahead and come up with what that radius is. The way I can do that is through Pythagorean theorem. Now, before I actually do, what I want to mimic here is the idea of the circle, just because I have the tool for it. Here's what your circle essentially, excuse me, hold on one second. How do I redo my undo? Here's what the circle itself would essentially look like, right? Maybe you can determine what your radius is just as a result of this, but this is what the circle will ultimately look like. It contains this point. So the idea here, which is the idea of the equation, this x minus h is really telling you how far away any point on your graph is from your center point h. This is your x minus h right here. What's that distance? 1, 2, 3. And then y minus k is how far up or down, your y point is from your k value of your center. This is 1, 2, 3, 4 right here. And that is, horizontal and vertical lines are perpendicular to each other. So what we can do is come up with the radius here, r, because this is a right triangle. We can use Pythagorean theorem to find out what that r is by doing 3 squared plus 4 squared equals r squared. And I'm going to save time right now. I'm going to tell you guys right now r is 5. You can go ahead and solve it by yourself using square roots and things like that. Not plus or minus 5, but just 5. What I want to mention here also is this is what's known as a Pythagorean triple. This is the 3, 4, 5 special Pythagorean triple triangle. Any other version of this that you see from me in any similar triangles, you're probably going to see me do that a lot instead of Pythagorean theorem. Anyway, the radius is 5. That is a 5 right there. That was important for this. We needed h and k. We got h as negative 1, k as negative 2, and r as 5. Now, when it comes to you in graphing, you would actually, because you don't have the circle tool, you'd have to still now count 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And you can see it's landing on them. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. And then you do the circle around that. And even that point. Heck, there are a bunch of other points you can find. Should there be a point that's 3 left and 4 up? Yep. 4 left and 3 up? Yep. All of these are radius 5, right? 3 squared plus 4 squared is 5 squared. Boom, boom, boom. So you could actually even probably make yourself a more precise circle just by knowledge of this. This is why Pythagorean triples are so great for that. You can get even more points around it if you wanted to. All these distances here are 5, as a circle would say it. Anyway, our equation is something I still need to write here. So I'm going to, up here, it's going to be x plus 1 quantity squared plus y plus 2 quantity squared equals 5 squared, which is 25. There we go. There's the graph, there's the equation. Let's move forward. Last page of review 1. Goodness, and I'm 40 minutes in. Let's find the same instructions. Find the equation, do the circle. But this time we need to find the equation to get the information. So you know the equation, it looks like this: x minus h quantity squared plus y minus k quantity squared equals r squared. Problem is, this doesn't take on this appearance right now. I don't have a factored perfect square trinomial quantity in the x minus h, nor in the y minus k. I can get there, though, by completing the square on my x terms right here, x squared plus 4x. Let's find a constant that'll make a perfect square trinomial for my x's. Let's do the same thing for my y terms, y squared minus 2y right here, plus this blank, equals, and then I'm going to go ahead and add this 4 over to this side, because I'll make it a part of my radius squared. But in doing so, whatever I add to one side, I have to add to the other side as well. Remember what we do for completing the square. This is a 1x squared. We're good. 4 divided by 2 is 2. Squared is 4. Negative 2 divided by 2 is negative 1. Squared is 1. So I'm going to add 4 and 1 to this side. And now I will factor this thing down right here. This becomes x plus 2 quantity squared. Right? 2 times 2 is 4. 2 plus 2 is 4. And we saw a version of this one. My phone just vibrated. I'm going to check that in a second. This is y minus 1 quantity squared. I think we saw a version of that a second ago. And 4 plus 4 plus 1 is 9. So this is the equation in standard form for the circle. This equation gives us our center and our radius. The center, remember, hk is opposite signs, right? So negative 2 comma 1. I think we had that as a center a second ago, right? And the radius is the square root of 9, which is 3. So again, equation gives us information, information gives us graph. Negative 2 comma 1 for center, and we'll go 3 up, 3 down, just like hopefully the Giants do today while pitching. And then left and right, like so. And let me rough out my circle. Yeah, there you go. You know, little pencil sketcheroos. Let's see what I got here. Oh, that was the text from my the person I need to tutor. Okay, sorry, doing these first. Okay, that's some circle graphs. I think we run across some others later as well. Can't recall for sure. Okay, these are things I'm not covering with my students in this current unit, but let's go and take a look at some. Graph each parabola, fill in and label all parts, show all work. Now, I do want to go kind of fast-esque on some of these things here. This is our parabolas that I've done with my kiddos before are right side up and upside down parabolas, up or down here. These are some y equals x squared kinds of equations. But you're looking at a form of x equals y squared here, which is either a rightward facing or leftward facing parabola right here. Not quite a function. It's just the opposite of what you would do with a y and x squared. So in this particular case here, I want to get x by itself. By dividing both sides by negative 8, I'll get x equals negative 1/8 y squared. Now, when it comes to me and graphing, what I like to do is think about the vertex form version of this thing. So in this case, it would be x equals a times y minus k quantity squared plus h. I can't dive way deep into why this is. I'm just going to go ahead and say that that's what it is. All that plus h. You don't see an h or k involved here. That means your vertex is 0, 0. As far as opening, up, down, left, or right, because this is an x equals y squared equation, opening either left or right. Because it's negative, we'll be opening left. I was going to say we'll be opening up left. It is absolutely horizontal for that reason. I kind of am going backwards and talking about that. So let's use those to graph, and then I'll talk about the axis of symmetry. Then we'll get slightly into focus and directrix, not in deep dive as to why, but we'll do that. So we're at 0, 0 right here. Now, if you're any good at doing stretch factor things with me, as I've said before, you remember for quadratics, we would do this 1, 1, 2, 4, 3, 9, 4, 16 kind of thing. But we would take the stretch factor, we'd divide everything by 8. And because we're going left, instead I'll do this 1, 1, 2, 4, 3, 9, 4, 16. But I got to divide those numbers by 8. 1, 1/8. 2, what's an eighth of 4? 1/2. 3, an eighth of 9 is 8/9. 4, 16, an eighth of that is 2. Sorry, 9/8, not 8/9. Let me do that again. 9/8. I said that's looking a little weird. 25/8, that's 3 1/8. 36/8, oh, these aren't fun numbers though. 36/8. I wish I could do 64/8. That one's 8. That would have been perfect. I'm going to go and fit that somewhere over here. 36/8 is 4 1/2. 7 is 49/8, which is, I'm spending too long on this than I need. 6 and an eighth. And then there's the 64/8, which is 8. When I go 8 up and 8 over, right there, doing the best I can. And reflecting here, 1/8, 1/2, 9/8, 2. That one's fine. 3 and an eighth, 25/8. 4.5, that's 36/8. 49/8 was 6 and an eighth, and then -8, -8 right there. All right, that's as perfect as I can get with you right there. I spent too long on something I'm not doing with my kiddos at all. Although the drawing's going to be a little squiggly. My apologies. Okay. The axis of symmetry is the equation of the line that would be cutting right through the middle of this vertex right here. And because it's a horizontal line, it's going to be a y equals equation. That axis of symmetry is y equals 0. Now, the focus in directrix. The focus is a point that is, I'm just going to be quick with it. It's a point that's inside your parabola that is p units away from the vertex. P is found by doing 1 over 4a. So, in this case, it's going to be 1 over 4 times -1/8. That's -1/8, excuse me, which is 1 over -1/2, which is -2. We will be 2 units to the left of the vertex right there to get the focus point. It is that point right there. It is -2, 0. The directrix is p units away in the other direction, and it is a line that goes perpendicular to the axis of symmetry here. So let me fade out the axis of symmetry a little bit. Let me get a little more of a, there we go, like that. And the directrix is a line that goes in this direction like such, and it is the equation of that line. It's 2 units away from the vertex, as you can tell, because the -2 that we got right there. And it's negative because of the focus direction. We go to the left there. But this is going to be x equals 2. That's the equation of your directrix. Now, in case you're curious, and I'm going to say this very fast, what is focus in directrix all about? We know how the circle has a center, and every point is equidistant from the center right here. They're the radius away. Well, every point on a parabola is the same distance, like this point right here. It's the same distance away from the focus as it is from the directrix, like that, the perpendicular line. That is congruent to that, and that is congruent to that, and that is congruent to that. These are all the same distance away from each other. That's what the focus and directrix are. All right, let's do the next question here. Same thing. Now, other people write these different ways. That whole 4p thing, some people write actually in the equation. This might be y squared equals 4px, I think. I'm not a big fan of that when it comes to graphing, so I'm leaving it. So I'm going to do the same thing as I did before. I want to make this an x equals a times y minus k quantity squared plus h equation. That helps me realize my own vertex, my own stretch factor, things like that. So let's do it. So I'm going to divide both sides by -8, and I will get x plus 2 equals -1/8 again, so I have to live with that. Y minus 1 quantity squared. Subtract 2 from both sides, x equals -1/8 times y minus 1 quantity squared minus 2. So once again, this is opening left. These are not very original. So this is going to be horizontal. It'll open up left once more. Your vertex, here's your h, here's your k. Remember, it's plus h, so vertex is -2. Minus k, so that's a 1. We've seen a lot of -2 ones in the past. Here's going to be another one. The axis of, well, and it's going to open up this way. So let's go and draw the same thing as before. 1 1/8, 2 4/8, 3 9/8, 4 16/8, 5 25/8. Wait, is that 3 1/8 one? Yep, 3 1/8. And 6 36/8. That's 4.5 right there. And other side, boom. That should be about 1/8, a half, 9/8, 2, 25 3 3.25, boom, 4.5, boom. That's all I'm gonna fit. Okay, there's your parabola. Same issue as before. I probably could have copied pasted my other and just placed it on the same vertex for my sake of time. Especially because you're doing the same one, you're not really getting much more out of what you just heard there. But again, I'm squaring the distance from the vertex, 1, 1, 2, 4, 3, 9, 4, 16. And I'm dividing them by 8, taking an eighth of them. Okay, Focus. Once again, the p once again is -2. I'm not going to change it from the last time. It's not, because the a is still -1/8. So my focus is going to be here, and my directrix is going to be here. It's going to be 2 away in both directions. So once again, they're not helping you very much in making different kinds of questions here. It's still a -1/8 thing going on. So, and it was still left facing. Every single thing was kind of the same there. So the focus is at -4, 1. The directrix is at x equals 0. And the axis of symmetry, by the way, this horizontal line right here, is y equals 1. Okay, let's keep going. All right, this is the next packet, if you will. And they tend to start off with proofs. Now, this is a different kind of proof. This is an algebraic proof. Ones that I didn't start off with my kiddos personally, but it's just a way of doing the algebra. And there's more than one way you can do this problem, by the way, algebraically. But it's just doing the algebra. I guess this is the given, right? But justifying each algebraic step. It kind of gets you into the idea of what proofs are, I suppose. So you're given this as an equation. There are two different things I could do next. I could either divide both sides by -4, which would be my ideal way of actually doing it. But as far as like maybe you don't recognize it, maybe it's not a clean division, maybe the number's too big for you to recognize how to divide. And for the sake of doing more practice and work with the reasoning, let's distribute the -4. If I distribute the -4, I get -44x minus 8 equals 80. That's the distributive property over addition, but the distributive property. Then I'm going to add 8 to both sides, and I get -44x equals 88. That is what is known as the addition property of equality. If you add something to one side, you must add it to the other side of equality. And then I use the division property of equality, divide both sides by -44, and I get -2. That is the division property of equality. Whoops, there should not be a period there. But whoever saw it. And that's it. I'm done. Solving for x. You got it right there. So that's the idea, guys. You're just justifying each step that you do. And I just did the algebra. It doesn't hurt to practice some algebra here. Likewise, I could have done this in, I guess it still would have been 3 steps. But I would have divided both sides by -4 instead to get 11x plus 2 is -20. Division property of equality. Subtract 2 from both sides. Subtraction property of equality. Division property equality. Again, divide by 11. X is -2. Okay, let's go to another triangle congruence proof. I think the first page of all these have some sort of proof aspects to them, so let's just look at it. NM is congruent to PQ as segments. NM is congruent to PQ. That is a given. And let's go ahead and mark that up. Boom, boom. It's showing that angle N is congruent to angle P. Angle N congruent to angle P, also given. Okay, we're eventually going to have to prove 2 segments are congruent. That will be probably through proving these 2 triangles are congruent and then using CP/CTC. We need one more set of parts, a third set, to show these triangles are congruent. I see vertical angles right here. We're going to talk about vertical angles, I'm sure, later. But I got these 2 different sets of angle L in both of these triangles. I have angle NLM there, congruent to angle PLQ. And that's the vertical angles theorem. Those are angles that are opposite each other when 2 lines intersect. They are always congruent to each other. That's the theorem at hand that I'm referring to. That's an angle symbol. And this is an angle side case, right? This is a case where I have angle side with angle side. These 2 triangles are congruent. And the fact that by the way, notice how we only use 1 letter for these because it's not, I'm certain that that's what I'm talking about, but I can't just call this angle L because there are a bunch of different things I can call angle L. So I'm going to use 3 letters when I have to, but it's a good thing that I corresponded parts NLM and PLQ because for my triangle congruence statement, I can just say the same thing. Triangle NLM is congruent to triangle PLQ by angle side, I believe I stated. There are problems on the bottom. The angle side congruence, triangle congruence theorem. That leaves me with segment LM congruent to segment LQ. This portion of this triangle is congruent to this portion of this triangle. These parts correspond. LM with LQ, they correspond with each other, 2, 3, and 2, 3. And the triangles are congruent. That is CP/CTC at play. Segment LM congruent to segment LQ by CP/CTC. And that is the final statement, and then we are done with that. Give me one moment. Okay. Skipping steps 6 and 7. There are no steps 6 and 7. Okay, find the value of x in each. This is where we're getting to some of the geometry aspects of things. I have two parallel lines cut by a transversal. This line cut by that transversal there, and it brings about certain angle relationship things. Now, I have no easier way to tell this to my students and to you guys than the following. When two parallel lines are cut by a transversal, angles will either be congruent to each other or supplementary to each other. Congruent means you set the measures equal. Supplementary means you add the measures up and set them equal to 180. Now, how can you tell when something's congruent and supplementary besides memorizing it, which is not a phrase I like to say ever? Well, this is pretty extreme enough, but let me go even more extreme. And I will ask you, just go based off acute versus obtuseness. Do these angles look congruent to you? Does this very acute, like 20-degree looking angle measure look like this 160-degree looking angle measure? Do they look congruent to you? Hell no. Do these look congruent to you? Hell yes, at least in comparison. They definitely don't add to 180. If these were both 160, 160 plus 160 ain't 180. The only way they could both add to 180 and be the same, or look the same, I guess, is if they were both 90. Or something along those sides. So there are certain angles, just go by the obviousness of it, especially based on parallel lines. They're mostly drawn as to scale as they need to be. Are they acute or are they obtuse? If that's as best as you can do to say whether they should be congruent, not if they're obtuse, they're congruent, but if one's acute and one's obtuse, they are not congruent. If they're both acute or both obtuse, then they are congruent. Are these two congruent? No. One's obtuse, one's acute. One's marked acute. It's 50. But when lines are parallel, these are called same-side interior angles, by the way. I'm going to abbreviate it SSIA. These are on the same side of the transversal right here. They're on this right side of it. And they are in the interior of the two parallel lines. They're in between. Same-side interior angles, much like same-side exterior angles, are supplementary to each other when lines are parallel. Now, there are other ways that I could talk about why that is. We can get into the triangle congruence, the theorems for them and proving these things. But I think it's just better off just saying, just look at them. You'll know, right? If it does help, if this is 50, so is this. That would be corresponding congruent angles. And this is a linear pair, which have to be supplementary. So anyway, these add to 180. We solve for x. 4x plus 40 equals 180. 4x, I'm going to go fast on the algebra. 4x equals, am I doing it right? 4x minus 10 plus 50 is 180. 4x plus 40 is 180. 4x is 140. Yes, x equals... Oh, I thought it was going to be a fraction. 4x equals 35, I believe. 35. I hope I didn't mess that up. Hope I don't go too fast on the algebra. Anyway, when lines are parallel, same side interior angles are congruent. All right, these ones right here. Do they look congruent? I hope you don't say no. Yes, they do. Remember, if they're either one or the other, congruent or supplementary, and supplementary means adds to 180, two very obtuse-looking angles cannot add to 180. Do they look congruent? Yes. If they're congruent, what do? Set them equal to each other. By the way, what are these angles known as? Alternate exterior angles. They are on opposite sides of the transversal, and they are both outside of their respective parallel lines. These are alternate exterior angles. When lines are parallel, alternate exterior angles are congruent to each other. You get x equals 8. I'll let you absorb that for a second. By the way, lines do not have to be parallel for these names to be what they are. Even if these lines are not parallel, if the lines look like this and cut by the transversal, these are still alternate exterior angles. They are just not congruent when alternate exterior angles are there. So that's important to state, because when we do proofs involving alternate exterior angles and things like that, we have to recognize that the theorem only holds up if the lines are actually parallel. Okay, let's move forward to numbers 3 and 4. I would say more of the same, but these are a little different. These aren't two parallel lines cut by a transversal. It's just two intersecting lines, and how do they relate to each other? Now, you might say, two intersecting lines? Mr. Robinson, these are three intersecting lines. Yeah, the only lines I care about are the ones that are formed by the angles. I have a 75-degree angle right here, and a 3x plus 6 degree angle right here. The 75-degree angle is formed by this line and this line. The 3 plus 6x degree angle is also formed by the exact same two lines. That means to me, this line is irrelevant. This line means nothing to me. All I want to focus on are the two blue lines. And what are we looking at when you have angles opposite each other? When two lines intersect, you're looking at vertical angles. What's true about vertical angles when two lines intersect like that? They are congruent. So I will set those equal to each other. Subtract 3, divide by 6, you get x equals 12. Here I do literally have two intersecting lines, only this time they do form that linear pair. A linear pair is they're not congruent, instead they're supplementary. It makes sense because this is a straight angle, it's 180 degrees, broken up into two parts. They're adjacent and supplementary. If they're supplementary, they add to 180 right here, by the way, LP, linear pair. 7x plus 15 plus 25 equals 180 this time. So add the 25 and 15, I get 7x plus 40 equals 180. Subtract 40, 7x equals 140. Divide by 7, you get x equals 20. Okay, those are some relationships right there. By the way, linear pairs and vertical angles can exist when you have two parallel lines cut by a transversal. These could be vertical angles, for example, and this could be a linear pair, for example, something like that. Has nothing to do with lines being parallel, by the way. Okay, numbers 5 and 6, and maybe a little 7 and 8. We're dealing with triangles, but in what capacity? Well, we have, first of all, the interior angle sum of a triangle is 180 degrees. That means if I had some x, y, z right here, then x plus y plus z would equal 180. That's true for every triangle, no matter size or obtuseness or rightness or anything else. They always add to 180. That being said, if I added some exterior angles, such as this W right here, and that's just by extending a side, just one side, W and Z would also add to 180, right? W plus Z is 180. They're a linear pair. We just spoke on that. They're a linear pair. Well, if X plus Y plus Z is 180, and if W plus Z is 180, these two things seem to be able to add with Z to get 180. What does that mean? Must mean those two things are the same. X plus y seems to equal w. Well, what are we talking about there? X plus y equals w. This is two interior angles and a remote exterior angle. The exterior angle that is not close to the other two, that is not adjacent to them like the z is. When you add those two remote, it's all relative when I say it, remote interior, remote exterior, they are remote to each other. The two interior angles x and y are remote to w, w is remote to x and y. These two remote interior angles added up equals the exterior angle, the remote exterior angle there. So, why am I pointing all that out? Because that's what we have here. I have two interior angles 30 and 4x plus 2. I have an exterior angle 8 plus 6x. When I add 30 with 4x plus 2, it equals 8 plus 6x. I'm saving my whole subtract this from 180 to get this angle and add these up to equal to 180 and solve. I don't want to work those backward steps to get right back to where I was. So 4x plus 32 equals 8 plus 6x. I'll subtract 4x over, I'll subtract 8 over, and I'll divide both sides by 2, and I get x equals 12 degrees there. Okay. Number 6, same thing. So I'll save you the something. Save you the lesson there. Add 22x with 15x, I get 37x, and plus 9. Subtract, oh goodness, you read a little too fast, you have a problem there. Subtract 9, is that 111? I hope this is 3. It looks like it, x equals 3 degrees there. Okay, there's some algebra there, and look, I'm going fast on the algebra. Combine like terms, move things over. You're in second semester based algebra now. If you're completing the squares, solving quadratic equations, doing things like that, you better be able to solve those. I'm going to say that here. All right, this is a right triangle, nothing to do with remote exterior angles, this and that. Solve for x, and then they actually say find the measure of angle A. So after you solve for x, I'm going to have to plug that into there and find it out, and that's fine. Now, all three angles in a triangle add to 180. That's true. In a right triangle, if this part's 90, this plus 90 is 180. Subtract 90, that means these two have to add to just 90. So I'm going to save myself one step in adding the 90 and set equal to 180. And I'm going to just set these two equal to 90. The two acute angles in a right triangle are complementary to each other. 2x plus 103 equals 90. 2x equals negative 13. X equals negative 13 over 2 or negative 6.5. Now, we're not done with the answer. And here's a couple things. I haven't solved this before on my own, but some students of mine had solved this before. Now that I think about this, and they stated, "Mr. Robinson, I think I did something wrong. I got a decimal. I got a negative." I mean, you can have fraction answers, right? That can happen. Can you have negative answers? You can have an x that is negative and that's 0. That's fine as long as the measures are positive. You can't have negative or 0 length or negative or 0 angle measures. And if you still do with correct math, then they wrote you a bad problem. This one is fine though. The measure of angle A is going to be negative 6.5 plus 43. 43 minus 6.5, right? So that's going to be, I think, 36.5 degrees. 36.5 degrees there. You got to put the degrees for that one for sure. Okay, number 8 right here. We got to solve for measure of angle A by solving for x. So right here you have an exterior angle in 72. 2x plus 18 is not an exterior angle because it is not an extension of just one side. It's an extension of two sides. Instead, it's actually a vertical angle with this angle right here. That means if this is 2x plus 18, well, then this is also 2x plus 18. And that's nice because now these are the two interior angles that are remote to this exterior angle. So I can use that remote exterior angle theorem one more time as I did before and add those two to equal the exterior. Add the two interiors to equal the exterior. 9x plus 18 is 72. 9x equals 54. X equals 6. Let's take that 6 and substitute it for x to find the measure of angle A. That is 7 times 6, which is 42 degrees. I hope I did my math right. Is that 54? Yes. 42. Okay. I'm going to take it. And then 36 plus... Oh, I'm sorry, that's a 6. I'm just doing... Okay, yes, that's correct. Okay. 9, 10, 11, 12. We have things with polygons here. Find the sum of the angles of each convex polygon with the number of sides. So if I have an 8-sided polygon such as this one, like an octagon. By the way, it doesn't have to be a regular polygon, meaning it doesn't have to have all equal sides and angles. But, you know, we have one right here. Stop sign, right? Or the octagon, little MMA fans, things like that. If you have this right here, what they're asking for you to do is say, what does this plus 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 this equal? And the concept is as follows. There's a formula we can use constructed by your understanding of triangles. If you took diagonals to this shape from a single vertex right here and broke this up into as many triangles as you can make, in an 8-sided shape, 6 triangles, then you notice that all the triangles here are made up of just interior angles that are comprised of your octagon's interior angles here. All the triangles have an interior angle sum of 180 degrees. We just learned that from the previous problems. How many triangles are there in here? 6. What's each of their interior angle sum? 180. What's the interior angle sum of the entire octagon? 6 times 180. 180 times 6. If D is 180 times 6, you get your value. Now that answers 1080. Now, I'm not going to draw this each time. In fact, I'm probably not going to draw it again. I probably will. But there's a formula involved in this thing right here, which I want to show you, actually, yes, by drawing. Oh, I can't do an 11-sided shape on my thing. Let me show you with another shape, though. Let me do a 6-sided shape, because we'll have to do it later over here. How many triangles can fit in a 6-sided shape? 4. There's a consistent thing to this because I'm drawing 2 less lines than the sides that have to go, right? I don't have to draw this side or this side. There are 2 less triangles than there are the number of sides in your shape. A 6-sided shape has 4 triangles. An 8-sided shape has 6 triangles. A 100-sided shape has 98 triangles in it. There are always 2 less triangles than there are number of sides. This 180 was really times 8 minus 2. Take the number of sides, subtract 2. Your formula is D equals 180 times n minus 2. If n is your number of sides, D is your interior angle sum. I'm giving you the basis of the formula so you know where it comes from and you know what to do with it. Anyway, 180 times 6 is 1080. The interior angle sum of any 8-sided shape, regular or otherwise, is 1080 degrees. An 11-sided shape, we're going to do the same thing. I just won't draw it here. D is 180 times 11 minus 2, which is 180 times 9. And my first calculation, I don't know off the top of my head, I believe it's 1620. 1620. So D is 1620, 1620 degrees. That is an interior angle sum of any 11-sided shape. And as it probably has become very prevalent, not only is it the more sides you have, the larger your interior angle sum is, but it's also every time you add a side to your shape, you're also adding another triangle, because the number of triangles is always 2 behind the number of sides that there are. And also going to these ones right here, if you have a regular polygon, such as what we were just referring to, I should not have deleted that. As you add the number of sides of any regular polygon here, the interior angle measures themselves also grow. You're not just growing the number of angles there are to add, you're also growing the actual obtuseness of those angles. Consider A, there's a 10-sided shape we have to do later, but consider A, what can I go to? A 16-sided shape. Look at that. It's almost a circle to you, right? There are more angles, and they become closer to 180. Closer and closer to 180 there. Anyway, there are 4 triangles in there, right? D is 180 times 6 minus 2, 180 times 4, which is 720 degrees. Now, they're asking, find the measure of one interior angle of the polygon. So if they all together add to 720 degrees, what is just one of them? If they're all the same thing, this plus itself 6 times is 720 degrees. If there are 6 angles that add to 720 degrees, then your interior angle, not to confuse the eye with the imaginary eye, you take your interior angle sum, divide by the number of sides. We do 720 over 6, which is 120 degrees each, right? 120 plus 120, etc. And that's the answer we're looking for in that case. So this formula, I is 180 times n minus 2 all over n, if you will. If you want to write it all like that, you can. I think that's a little much to bring about, but you totally can. You put d over n if you know what the d represents. All right, 10 sides right here. I don't know if it's the last one to do, but you want to go straight to formula? I equals, I don't want you to memorize and then therefore mismemorize. That's going to be a really big hassle. I especially don't want you to misconstrue what it is you have to do here. This can help you in the long run, though. Check this out. I can do 180 divided by 10 to get 18. Boom. And then I can just do 18 times 8. I don't really like that number, actually, now. 18 times 8 is, I think, 144. So 144 degrees. I'm just going to go ahead and say it is. I believe it would be there. Okay. And there's the answer for that one. Okay, new concepts. 2 sides of a triangle have the following measures. Find the range of possible measures for the third side. To make best sense of this here, you first have to understand what the triangle inequality theorem states. If I have 3 sides of a possible triangle AB, of any triangle A, B, and C, assuming C is the largest side of the triangle, for my current statement I'm going to make here, adding up the 2 smaller sides has to be greater than the third side in and of itself. Unlike Pythagorean theorem, where a squared plus b squared equals c squared for any right triangle, here a plus b must be greater than c for any triangle, period, including right triangles. And really for any sides, but you want to test it for the 2 smaller sides against the biggest side here. Case in point, and we're not testing these, unfortunately. Let me just bring one about here. Let's say this number was 25. Can I make a triangle using these 3 values here? You're going to say yes, because 14 and 25 being 2 smaller sides than 30, 14 plus 25 is indeed greater than 30, because that's 39. 39 is greater than 30. You have to think of the physical idea for that, right? They need to be long enough to be able to bend, yet connect to make that third side length. If I had a side length, though, such as 15, that falls just short. 14 plus 15 is not greater than 30. That's 29. That ain't greater than 30. That doesn't work. See, if I had a side length that was 30, and here's like 14 and here's 15, oh, it doesn't reach. It's not far enough. You can bend it down more and more, but the simple fact is, even at straight values, they only get as far as 29 units. So you can see how they don't connect. But you also don't want it to be too big that it becomes the biggest side of the triangle, such that 14 plus 30 isn't greater than it. So here's the thing. There's a range of possible measures for the third side. I'm going to place an x into here and say, what can x become? It can become this small, yet this big. There's an x value that we can put in between. You saw that 25 worked. You saw that 15 didn't. What other numbers do work? What other numbers don't? Let's test them as inequalities the same way we would here. Treat x as if it's one of the short sides with 14. I need one of the short values with the 14 to add up and still be greater than 30. Right? That's one of our conditions we need to do. It's short enough, long enough, even as a shorter value, that when I add it with 14, it's greater than 30. Subtract 14 from both sides, x would have to be greater than 16. So there's your answer. It can't even be 16. It needs to at least be like 16.1 or whatever, or 17, whatever it is. It needs to be greater than 16, for if it's not, it is too short. So that's one condition. That's the shortest, not even the shortest it can be. It can't be it must be greater than 16. But it also can't be too long. Consider if x was a longer side, like, could it be 40? Yeah, because 14 plus 30 is greater than 40. How big can it get? 14 plus 30 has to be greater than the number, whatever it is. What is 14 plus 30? Well, it's 44. So 44 has to be greater than x. Better yet, x has to be less than 44. So there's kind of an and scenario here. X needs to stay within, it needs to be greater than 16 and yet less than 44. It needs to be greater than 16 and yet less than 44. The best way I like to write that is as a compound inequality, x must be between 16 and 44. And as long as it is, you can make a triangle. Any number in between, decimal or otherwise, can make your thing a triangle there. And that's what you do, 2 different tests. Notice I didn't test to see if x plus 30 had to be greater than 14, because 30 is already greater than 14. There's no reason to consider that one. So there's the theorem itself. Let's try it for the second problem right here. 17, 19, and some x. If you treat x as one of the smaller sides with 17, x plus 17 has to be greater than 19. And yet, treat x as the largest side, 17 plus 19 has to be greater than x. In this case, if you subtract 17 both sides, x must be greater than 2. And if you add these together here, 36 has to be greater than x, or x has to be less than 36. Better way to kind of put it, so you're not comparing the wrong way there. So x has to be between 2 and 36. That's a nice wide range right there of values that is possible. By the way, as you write a compound inequality, please always write it from smallest to greatest right here, your variable in between, as we put it. And yeah, never flip it over. Don't put 36 x 2. That's just not the syntax. That's not how we say things. X isn't between 36 and 2. It's between 2 and 36. And there you go. Okay, number 15 right here, and 16, and yep, 15 and 16. We are dealing with isosceles triangles. An isosceles triangle is a triangle with not only 2 congruent sides, but also 2 congruent angles. Those angles are opposite those congruent sides right here. These would be known as base angles right here. This is known as a vertex angle. This is known as the base, and these are known as legs. I'm saying all that. I should probably write all that, but I'm probably going to erase all this at some point as well. I bring these things up because I'll probably say these at some point. Angle and base angles. But I'm probably going to bring them up in terms of terminology. Now, your triangle doesn't have to be base on the bottom. It's just base is the one that makes up the base angles. The base angles are opposite the congruent sides, your legs. Case in point, I have the legs right here. Opposite this leg is this angle. Congruent to opposite this leg, this angle. These are your base angles. If this is 54, this is 54. They want us to solve for x here, and all 3 angles in a triangle add to 180. So 54 plus x equals 180. 108 plus x is 180. Therefore, x equals 72 degrees. There's the algebra. There's the setup. There we go. Number 16 is another set of isosceles triangles. We got to solve for this x. It's kind of, you got to navigate a little bit, do some strategy here. Let's work out this triangle, because if we can get these angles here, then we can use this angle as a vertical angle pair to get that, and then you can work in this triangle here. So this isosceles triangle, here are my legs. Here are the base angles, each 65. I'm going to save you a little bit of work here. 65 plus 65 is 130. 180 minus 130 is 50, right? These all have to add to 180 there. So there you go, 50. If this is 50, then that's 50 right here. Vertical angle pairs, right? Here's another set of isosceles triangles here. If this is 50, then this is 50. Those are my base angles. And 50 plus 50 is 100, plus 80 is 180. X is 80 degrees there. Yeah, I didn't show the work. Well, here's work, but I didn't do algebra every single time out. Sometimes I think just with more strategy involved is probably worth working in a different realm, and that was it. Okay, Number 17 and 18, we have parallelograms for each of these here. They ask you to solve for x. Now, there are some properties of parallelograms that I think we should know going into this set here. What are some properties of parallelograms? Well, let's start with the definition property. I don't think it applies to this particular set of problems, but by definition, opposite sides of a parallelogram are parallel. That can help for angle measure problems. You have alternate interior angles, something like that. But opposite sides are also congruent, and I think that has to do with our first question we have here. Opposite sides are congruent. We saw that if you were watching on the very first problem about definition of a rectangle, opposite sides are congruent in a rectangle because a rectangle is a specific type of parallelogram. And it will inherit all the properties it has. A few other properties here. Opposite angles are also congruent in a parallelogram. But the consecutive angles are supplementary. Consecutive angles meaning ones that are right next to each other. And that makes sense because those are the same things as same side interior angles. If this line is parallel to this line, these two lines cut by this transversal, I got same side interior angles right here. Boom and boom. They are supplementary when lines are parallel. And that kind of seems to make sense for that. And lastly, the diagonals bisect each other in a parallelogram. Diagonals bisect each other. And when I say diagonals, I am referring to the segments drawn from opposite angles. SU and TR, they would break them up in such a way that this would be congruent to that and this would be congruent to that right there. Now, there aren't diagonals in this problem. That's not relevant to the problem itself. Here, we're going to talk about opposite sides congruent. Because 2x plus 15 equals x plus 15. Well, that sounds weird. What value of x could you be? That you're adding 15 to both of these, but one's multiplied by 2. Subtract x from both sides, subtract 15 from both sides. X equals 0. What? Mr. Robinson, I did something wrong. Mr. Robinson, you did something wrong. Mr. Robinson, what went wrong? Well, plug in 0 for x. See what happens. 2 times 0 plus 15 is 15. 0 plus 15 is 15. They're still 15. They're congruent to each other. That's what we wanted. 0 is the value of x we were looking for. All right, number 18. These aren't side lengths, and that's not one string of an expression. These are two different angle measures. 9x plus 15 degrees here, 6x plus 15 degrees here. Those are consecutive angles. Consecutive angles in a parallelogram are supplementary to each other. So I add this with this here, and you set it equal to 180. Let's do the fast algebra right here. 15x is 150 divided by 15. You get x equals 10. Put the degrees there. So you add those to 180 because they're supplementary. If this was 6x plus 15 down here, you would set them equal because opposite angles would be congruent, but that's not the case. Okay, we're getting back to some triangles, but in a different way here. We're going to talk about similar triangles. Let's find the missing lengths of these triangles where they are telling you they're similar, and we're going to have to fall under a pretty straightforward pretense of which parts should correspond with each other. Anything that's on the bottom corresponds with something else on the bottom and things like that. We're going to have to just go with it. That's okay. Now, when it comes to triangle similarity, all similar triangles mean is, I'm trying to build you two of them right now, is one is just a bigger version of the other. So these two triangles are similar to each other. This one is just a bigger version of this one. Now, what's true when things are bigger, when I say bigger, I'm talking about side lengths, right? This is like 1, 2, 3.5 of these and whatever. And the idea is it grows the same amount in every which direction. I guess it's not truly similar here. I have to, there we go. That's a little better. Maybe this is like 1, 2, 3 times its size, right? 1, 2, 3, 1, 2, 3, 1, 2, 3 times its size. Great. The angles stayed the same. This angle is the same. This angle is the same. This angle is the same. In similar triangles, corresponding angles are congruent, but corresponding sides are proportional. Proportional means that they grow by the same amount. Once again, whatever this length is, this is 3 times it. Whatever this length is, this is 3 times it. Whatever this length is, this is 3 times it. We can set up proportions to say when I divide one side by another corresponding part, I get 3. For each of them, they would all have the same similarity ratio, and you can do the same thing here. I got to find this length here, this PW length. I'm just going to go ahead and call it X because I'm going to work some stuff out algebraically. I don't like a question mark, and PW is just too fanciful. So what we have to do is find parts that correspond. We have to construct it in such a way that we can come up with a proportion to set things equal, such as x represents here, which we have to use at some point, the bottom side of the small triangle. When I divide it by, say, its corresponding part, the bottom side of the big triangle, 22, I get some similarity ratio. X is so many times smaller than 22. How many times smaller is it than 22? It's the same amount smaller than 22 as, say, the right side of the small triangle, 6, is compared to the right side of the big triangle, 12. Whatever x divided by 22 is, 6 is divided by 12. Or 12 divided by 6, 22 divided by x. There are some things you can probably see point blank right now, which is 6 is half of 12, therefore x is half of 22. You know what x equals? 11. And you know what? That's correct. And if you want to stop right there, especially on a multiple choice final, go ahead and do it. That's perfect. That is using that's doing more than just here's a formula, go ahead and do it. That's using logic and reason. The problem is the math isn't always that easy for us to do that, and we have to sometimes do a little bit more, for which I will probably do here. One version is cross multiply 12 with x, and I'm just going to assume you know what cross multiplication means and why we do it. I know some teachers act against it. I sometimes do. But the fact of the matter is, we can do some magic steps in math if we know what they are. 22 times 6, 132, I think. And then divide by 12, you get x equals 11. Obviously, same answer. You're going to see me do more often a fraction reduction. I would turn 6/12 into 1/2 immediately to cross multiply to get 2x equals 22. Therefore, x equals 11. And I know I'm doing a lot of you can do this, this, or that. Obviously, I want to move off this pretty soon, but there's more than one similar triangle bit we'll do, and I want to do the fastest way possible later. So I want you to know what it looks like now. And the other one that we can totally do here, besides just this proportion, is I could have corresponded it with the top sides of the triangle right here. What did I say here before? This dialogue matters. I want you to listen to this. The whole side of the bottom side of the small triangle corresponds with the bottom side of the big triangle. Therefore, the top side of the small triangle corresponds with the top side of the big triangle, the whole side. Not just this 9 right here, but this 18. So x over 22 also equals 9 over 18. And I mean, that makes sense. 6/12 is 1/2, 9/18 is 1/2. These all correspond in that way. Now, there are other versions of this that you can use, and I will probably use it on number 21 over here. We will see. There are just different versions, but it's known as the side splitter theorem, which means if I can split the side of the big triangle right here into just this WR, that this divided by this also equals this divided by this, for example, as long as you correspond to split part of the big triangle. A lot of different things we can do, guys. A lot of different things we can do. X equals 11. Number 20. Let's fall into the assumption once again that the bottom of this corresponds with the bottom of that. Generally, that's not a good assumption to have. I'd like to have the similarity statement, but I believe that to be so, what they're doing here. See, this time, 42 corresponds with 28. Well, how much bigger, how many times bigger is 42 than 28? I happen to know it's 50% more. I know it's 1.5 times bigger. You might not. So it's better to kind of work out that proportion in that way. By the way, I can feel these triangles as being similar in those parts corresponding because this 35-degree angle measure corresponds with that 35-degree angle measure. So I definitely get that feeling that these are the corresponding parts we need. Anyway, if this was an x here, whatever 28 over 42 is, whatever the top side of the small is to the top side of the big, the bottom side to the small is to the bottom side of the big, x is to 33. And yeah, before you do cross multiplication, now going this way, this is 2/3 of that. 2/3, we got to take 2/3 of 33. You could cross multiply and divide. You could multiply both sides by 33. I don't care, guys. It's algebra the rest of the way. I'm helping teach the geometry for you. You should know cross multiplication through proportionality through the previous year. Well, let's just play cross multiply. 3x equals 66, x equals 22. And I'm not saying that in a stubborn way. I'm saying it in a, I'm already an hour and a half into this thing and I'm still on the second review worksheet out of 6. So, you know, I'm going to work on what it is I feel I need to work on. And obviously, I'm probably over talking compared to what I thought I would. All right, number 21. Once again, so many different ways you can go about this. I don't know which one's best. I don't know if it comes to explanation of what's here. Let me talk some things out. Here's one you can do that's a little bizarro. You can compare x to 12. That's fine. I can say, hey, guys, x over 12 equals, as long as you know what corresponds in the other parts. X is a split part of this bigger triangle here, and 12 is the whole part of the big triangle, which uses this part of the small. 18 is a split part on this side of the big triangle here, and I can work that as long as I now work the whole part here, 24, 18 plus 6, and correspond it with that 12, right? It works in that way, that this over this equals this over this, right? There are versions of this you can do. That's why I'm saying so many ways. There's not just one way you can say, but here's one setup. I'm going to go ahead and let you solve that way if you'd like to. Let me show you the side splitter theorem, though, and just show you a different approach in case you have to run into this other version. And it's this. I'm still calling this x, but I want to express this. I want to find a length for this. That would be 12 minus x. You take the whole length and subtract that, right? So here's side splitter theorem. This over this equals this over this, also known as triangle proportionality theorem. 6 over 18 equals 12 minus x over x. And again, there's so many ways you could write it. I could have done 18 over 6 is x over 12 minus x. 6 over 12 minus x equals 18 over x. As long as it's the split parts with the parts that naturally correspond. I would not do 18 over 6 equals 12 minus x over x. 18 does not correspond with 12 minus x. Anyway, let's move on. 6/18 reduces to 1/3. You cannot cancel out these x's for any reason. I hope you know why. Let's cross multiply here, and 3, here's x on this side. 3 will multiply with 12 minus x, like this. This is one reason I wanted to show this. You distribute the 3, and you get 36 minus 3x. I add 3x to both sides. I divide both sides by 4. You get x equals 9. You should get x equals 9 if you solve it this way as well. This is probably the easier way to go, but you got to know how to do it. You got to know what it looks like. And triangle proportionality works because the triangles are similar. Moving on. Let's do, this is part 3. Let's do another algebraic proof and another geometric proof. The algebraic proof here will fall in line pretty similarly to what the last one was here. I'd love to start with distribution right here. Oh, sorry, I'd love to start with the given. Hope they give me enough steps here. That is given. I notice when I start writing more and more over time, my G's get kind of bad there. Let's distribute and get 21x minus 27 minus 19x equals negative 15. That is done by the distributive property. I shall combine like terms here. 21x minus 19x is 2x. Combine like terms, simplification. Now I will add 27 to both sides. Adding 27 is the addition property of equality. Addition property of equality. And then divide both sides by 2, you get x equals 6. Good, 5 steps. That is the division property of equality. I mean, it's algebra, but I'm giving you the actual reasons to them as well. All right, let's do a geometric proof here. Given QP is congruent to TQ. Wait a second. QP is congruent to TQ. That's probably TP. TP. And then RP is congruent to SP. Let's prove that angle R is congruent to angle S. Let's start with our givens. QP congruent to TP. And then RP congruent to SP. Given, given. See, there's another bad capital G. Okay. We want to prove the triangle's congruent and use, therefore, a CP-CTC measure on R and S. Eventually, we're going to get to that and that. But until then, let's see what we can add. Vertical angles are congruent right here. And let's try and get the proper corresponding parts so our triangle congruent statement can keep the same letter order. Let's call this one QPR. And the other one, do I call it SPT? No, I want to call it, see, QPR goes across the 1 congruent tick mark and the 2 congruent tick mark. So let's go across the 1 and the 2. Let's call it TPS. Angle TPS, that's the vertical angle theorem. It's not incorrect to do the other one until you do the triangle congruent statement, but you might as well work corresponding parts as often as you can. I really do believe that. I think it's more consistent. It keeps you in that mindset of doing it. So now the two triangles are actually congruent to each other. This is a side angle side case. Triangle QPR is congruent to triangle TPS. This is by side, angle, side, triangle congruence theorem. And therefore, angle R will be congruent to angle S by CPCTC. R and S do correspond, as you can tell in my triangle congruence statement. They're both the third letter each. The triangles are congruent to each other. Therefore, the angles are congruent by CPCTC. Proven. All right. Find the missing length, leave answer in simplest radical form. So what we're doing here, this can get a little picky, and I can talk about it in a lot of different ways. I'm going to try and do the best I can with in brief order. You have you have a right triangle here. You notice this big guy right here. You have a right triangle here. I'm going to call it the big right triangle. When in that big right triangle, you draw an altitude right here. It constructs another right triangle right here. I'm going to call it the medium right triangle. Let's do that again. I'm going to call this guy the medium right triangle. If you notice, if I do some things to this. Let's see. And then I have a small right triangle right here. Okay? So I have 3 different right triangles. These right triangles are similar to each other. For one, they all share a right angle right there. Big, medium, small. But they also share congruent other angles. See that? These angles here are congruent, and these angles here are congruent. So the triangles are similar, right? They're different sizes, small, medium, big. But they are similar, therefore they share corresponding parts. Notice they all have a short leg, short leg, a long leg, LG, short leg, long leg, and a hypotenuse. The short legs all correspond with each other. The long legs all correspond with each other. The hypotenuses all correspond with each other. In the small triangle, I have short leg, long leg, hypotenuse. In the medium triangle, I have short leg, long leg, hypotenuse. In the big triangle, I have short leg, long leg, hypotenuse. If you can find corresponding parts in each of these, you can build proportions to end up solving for an angle measure. Sometimes you can use Pythagorean theorem, I'm sure, to solve for things. There's sometimes more than one way to solve these. And I can also possibly talk about what are called geometric means. I can't get too deep into the nature of what geometric mean is, other than to state that some legs are sharing parts. For example, let me state this because we're going to do it right here. X is not only what we're solving for, but it is also representing both the short leg of the medium triangle and the long leg of the small triangle, right? This and this are both X right here. That's X and that's X. And you know, in this big triangle here, the short leg of the big triangle is also the hypotenuse of the small triangle. And the long leg of the big triangle is also the hypotenuse of the medium triangle. So there are shared parts in these. And what's good about that is those construct what are called geometric means, where it is the in-between value of 2 other parts that you build in proportion. I can correspond X as the, let's say, the long, let's see how I'm going to say it, the short leg in the medium triangle. X is the short leg in the medium triangle. And I can correspond it with the short leg in the small triangle right here as 9. The short leg in the medium divided by the short leg in the small. You know what else I can do? X also represents the long leg in the small. Now let's get the long leg of the medium. Long leg of the medium is 25 minus 9, that's 16. So it's 16 over X right there. Short leg of the medium over the short leg of the small equals the long leg of the medium over the long leg of the small. And my students have a lot of trouble coming up with that thing. And I know there are formulas and stuff we can come up with. One of them is, some of them I'll talk about. But it's your corresponding parts. If you want to redraw the triangles, you can. If you want to say out loud what these parts are, you can. You find the parts that correspond in these similar triangles. Anyway, this is our setup. Cross multiply, take the square root, you get X equals 12. Now, that's how we go about solving these problems here. Now, I really did need the 16 for the problem, so I'm going to keep 16 here as well. Here's the way I'm going to tend to talk about these, because anytime I run into it, I would love to. X is the geometric mean of 9, 16. Geometric mean means in a geometric sequence, such as this, You multiply 9 by some number to get x. You multiply x by the same number to get 16. What number is that? Whatever you divide 16 by x with, and whatever you divide x by 9 with. 16 divided by x with, and x by 9 with. And those are equal. Or 9 divided by x, and x divided by 16. This over this equals this over this. If x is the geometric mean, then it's the part that's in the middle of these two size-wise. That's how that works here. 15 is also the geometric mean of two parts. It's harder for me to bring up what it is as geometric mean. It's kind of harder for people to look at it this way. But what I will do is my corresponding parts bit. 15 corresponds to two different parts in two different triangles. 15 is the short leg of the big triangle. And that can correspond to the short leg of another triangle, such as your 9. Short leg of the big over short leg of the small. Okay, let's do something else in the big, something else in the small. What else do we have? We have the hypotenuse of the big, x plus 9. Do we have the hypotenuse of the small? You betcha, 15. 15 is the geometric mean of 9 and x plus 9. A little harder to say. I think people kind of wrap it around the triangle to talk about it that way. Not going to do that. Cross multiply. Well, you know what? Let's reduce this right here. Reduce. 5/3 and x plus 9 over 15. All right, cross multiply right here. We're going to get 3 times x plus 9 equals 75. That's 5 times 15. 3x plus 27 equals 75. 3x equals, I'm bad at math. 48. X equals 16. X equals 16. Moving on. Two more of these right here. Solving for x, leaving simplest radical form if we have to. So x is what we got to find right here. That's that whole hypotenuse. Sometimes it's best to look at that. Find your x, ask yourself what part it is, and ask yourself, is there a corresponding part in another triangle that we have? Okay? X is the hypotenuse of the big. Do we have the hypotenuse of any of the other triangles? Yes, 60 is the hypotenuse of the small. So we're going big triangle to small triangle. We did the hypotenuses of each. Do we have something else in the bigs, right? Big to small. Let's go big to small again. Do we have another part in the big triangle that we have? Yes, the 60 again. That's the short leg of the big. Do we have the short leg of the small? Yes, that's 36. Hypotenuse of big, hypotenuse of small. Short leg of big, short leg of small. I'm sorry, give me 1 second. I have to respond to this text. Hold on. Okay, I'm back. I didn't solve. I hope the last thing it talked about was the corresponding parts. Okay. Before cross multiplication, consider fraction reduction. I can divide these by 6. I can divide them by 12. I'll get x over 60 equals 5 over 3. And you know what? Sometimes forget cross multiplication. Let's just multiply both sides by 60. I mean, we're going to divide by 3 anyway, right? What's 5/3 of 60? 60 over 3 is 20. 5 times 20 is 100. I mean, you know, spend the time that you need to spend on a problem, and you know that's what it is. You're actually going to see me do some of the, well, actually, I don't know. You know, some of the review, just to make mention, because we're talking about triangle similarity right now, we're not proving any triangles are similar on this review. I'm sorry, they just don't exist in the reviews. I didn't make them. They just don't exist. And we're also not going to get any, when we talk about the circles, there aren't any questions in this review on arc length or sector area. And something that I was going to say we'll do there, we don't have those questions on there either. So you have to look at some of my other videos for that. They're pretty recent, though, where I did do them, so maybe you can find them. Okay, and the last one right here, you know, x, once again, what we're trying to solve for, it represents two things. It represents the hypotenuse of the small triangle and the short leg of the big triangle. So let's consider the hypotenuse of the small triangle. It's the hypotenuse of the small, and we also happen to have the hypotenuse of the big in 25. They correspond. Whatever they divide by is the same thing as, what did I say? Hypotenuse of small, hypotenuse of big. Let's go of the small. It's the, the short leg of the small. We have the short leg of the small, and we have the short leg of the big in x, right there. This time when we cross multiply, it's an x squared, and that equals 225. Let's take the square root. X is 15. Okay, time is going now. All right, get your calculators out, folks. We are going to be working with trigonometry. I don't have to use a calculator for this one, but find the value of each trigonometric ratio. So this is all about SOHCAHTOA. Sine, taking the sine of an angle is the opposite side of the angle divided by the triangle's hypotenuse. Cosine of the angle is the leg adjacent to the angle divided by the triangle's hypotenuse. The tangent of an angle equals the ratio opposite that angle divided by the adjacent leg to the angle. Let's take the tangent of z, TOA, angle z right here. I don't need to find the angle, I just need to write what the ratio is. Tangent of this angle is opposite over adjacent. Tangent of z is 21 over 28. There is the answer. Reduced is 3/4. There's a better answer. But there's the answer right there. It's just the ratio, or 0.75. They might say that, 0.75, but there it is. The sine of c, sine is opposite over hypotenuse. The sine of the angle here is 24 over 40. And, as I'm saying this stuff here, I'm sure my students know how to do this, and I'm sure you guys watching know how to do this here, 3/5. I still don't know if you guys know what it means when we say sine, cosine, and tangent. I try and explain it as best as possible. They're just three different ratios to represent triangles for the parts that you have. But it's basically a way of saying when you take the sine, cosine, and tangent of an angle, you get a ratio. These are similar right triangles. When you have those angles, I don't know. I'm going to stop. I sometimes wonder if they know what it actually means when it's being asked to do that. But here's a reason we use it. To find missing sides and such. Your calculator, when I'm going to do a computation and get your approximated x answer, it understands what the tangent of 41 means and how it's represented to get this. And I'll try and explain it here. Round to the nearest tenth. And I'm going to use tangent. This is an angle for which I know the side opposite and the leg adjacent. That's TOA. Tangent of 41 degrees is equal to 4 over x. I multiply both sides by x, I divide both sides by tangent of 41, x equals 4 divided by the tangent of 41. Now that is an exact answer. Approximately, let's go to the calculator here, you need to make sure your calculator is in degrees. Mine's in radians. You need to make sure your calculator is in degrees. And I'm going to do 4 divided by tangent of 41. By the way, I'm not going to show my calculator for every problem. And I'm going to get 4.6-ish. X is about 4.6 units. Okay, so a couple things with the problem before I move on, and I promise to go fast with the rest of them here. Tangent of 41 is a number. Actually, let me show you what that number is. Tangent of 41 is this number here. What does that number mean? It means that in a right triangle with a 41-degree acute angle measure, the side opposite divided by the leg adjacent will equal this amount exactly. Don't believe me? Let's do 4 divided by that previous... Oh, how do I do this? Let's do 4 divided by that previous answer. Well, I can't do this. 4 divided by 4.6 is this number here. Not exactly 4.6, but approximately. Is that number there. It's the same ratio. Tangent of 41 is just some number. It's the ratio that divides the side opposite divided by the leg adjacent in any similar triangle, right triangle with a 41-degree angle measure. That's as best as I can say. All right, number 8 here. With the 47, I have the leg adjacent and the hypotenuse. I'm going to use cosine. The cosine, see, I get in trouble when I overteach. Not like I get reprimanded. I mean, I spend too long talking about it. But I want someone to make sense of what they're doing before they make a mistake on something. Now, what did I just do here? I multiplied both sides by 3. Multiplied both sides by 3. So x is 3 times the cosine of 47. I'm going to my personal calculator now for this one because, I'm in degrees. I'm in radians on that. 3 times cosine of 47. I'm getting 2.04. So I'm going to say that is 2.0 units right there. By the way, just some double checks on both of these things. Some ways to, maybe you don't know that you're right, but you can know if you're wrong sometimes. I trust my 4.6 answer right here because it should be more than 4. Because this angle is 49, and something that we got to get into at some point here, that sides opposite smaller angles are smaller. How do I say that? A side opposite a smaller angle is shorter than a side opposite a larger angle. How do I know this is 49, by the way? Because he's got to add to 90. So this should be more than 4, is basically all I'm saying. This is the hypotenuse of your triangle. This should be the largest side of your triangle. So having 2, I guess, is fair enough for this one. It should be less. Okay, number 9. With the 37-degree angle measure, I'm looking for the side opposite, and I have the hypotenuse. That's sine. Let's take the sine of 37, and that's going to equal x over 10.3. Algebraically, if we multiply both sides by 10.3, we get x equals 10.3 times the sine of 37 degrees. Calculator ahoy, me hoy. 10.3 times the sine of 37, and we get 6.19, so 6.2. X is about 6.2. And lastly, we have 50.1 degree angle, opposite and adjacent. We're going to use tangent. Tangent of 50.1 degrees. It equals opposite over adjacent, right there. Multiply both sides by 5. X equals 5 times the tangent of 50.1 degrees, which is about, well, here's the thing. I expect it to be more than 5. I expect it to be more. I don't know how much more. Tangent of 50.1. So 5.97. So around 6.0. Right there. Okay. More trig. You could use trig, but they're, not really at the same time. No trig. No capes. This is more similar triangle stuff. Find the missing side lengths. Leave your answers in radicals in simplest form. No decimal answers. That means no calculator, no trig, no capes. There's one way. If you did know what the sine of 60 was, then you could technically use trig. But the idea is going to fall in a different way. We're going to do it in the way of knowing our triangle similarity of what are known as special right triangles. We have 2 special right triangles to consider. I'm not going to get deep into the reasoning. We'll just talk about what I'm going to do with it. I got a 45, 45, 90 triangle and a 30, 60, 90 triangle. These are special because the sides compare to each other in very clean-esque ways. Like in a 45, 45, 90, that's also an isosceles right triangle. So opposite, these angles are equivalent. If this was 1, then this is 1. I'm shortening. I could call them x. I can call them 2. I don't care. Whatever one is, the other is. They fall in a 1-to-1 ratio with each other. That's nice. If you use Pythagorean theorem, you find out the hypotenuse is the square root of 2 times larger than either of those. My point that I'm making is, in any 45, 45, 90 triangle, because they're all similar to each other, the hypotenuse is always the square root of times larger than either leg. And the legs are the square root of times smaller than either hypotenuse. Legs are equal to each other. So if I want to go from a leg to hypotenuse, I multiply my length by the square root of 2. If I want to go from hypotenuse to leg, I divide by the square root of 2. Simple enough. In a 30, 60, 90 triangle, let's equate in a similar way here. 30, opposite the 30 should be the smallest side. I'll just give it a 1, so we know the numbers that we see here are how many times larger they are than the 1. The hypotenuse is actually double that of the shortest leg, and the long leg, which is smaller than the hypotenuse, is actually the square root of 3 times that of the shortest leg. The way I call this one is 1 to 1 to root 2. The way I call this is 1 to 2 to root 3. It's kind of an upward counting thing. This one you can kind of know better by being isosceles and Pythagorean theorem there. This one you count 1, 2, 3. Only the 3 has a square root to it. And root 3 is smaller than 2 because 2 is the square root of 4. And the square root of 4 is, more than the square root of 3. So opposite the smallest side is angle is the smallest side. Opposite the largest angle is the largest side. And long leg, middle angle in between. So anyway, if you wanted to find out any lengths here, to go from the short leg to the hypotenuse, you double it. To go from the hypotenuse to the short leg, you halve it, divided by 2. To go from the short leg to the long leg, you multiply by root 3. To go from the long leg to the short leg, you divide by root 3. And I would go in that fashion. I wouldn't go from long leg to hypotenuse. That's kind of a 2-step process. Might as well get the short leg in between. Okay, what are we going to do here? Very straightforward. I have a 30, 60, 90 triangle right here because the 60 and the 90, therefore this is 30. This is the short leg. This is opposite the 30. The long leg is root 3 times larger than the short leg. It's 5 root 3. The hypotenuse is double the short leg. It is 5 times 2, which is 10. That's it. This is another 30, 60, 90 triangle right here. And I do have, once again, opposite the 30. I feel like I'm giving you easier, I didn't make these, but I feel like you're getting easier versions of these problems where it doesn't look like you're simplifying any radicals, you're going from hypotenuse to long leg or anything like that. Apologies on that. I hope we run into something down the line. If not, find other review videos that I have or that other people have. They'll probably work the same thing. By the way, I could make proportions out of these, but I'm saving you time and just saying we know how many times larger it is through this ratio relationship. Let's just call it out. Let's go from the short leg to the hypotenuse. Let's double. This is the hypotenuse, by the way. It's opposite the right angle. 6 times root... Oh, excuse me. Let me get rid of that. 6 root 3 times 2 is 12 root 3. That's your hypotenuse. 6 root 3 times root 3. Ooh, let's write that out. N is 6 root 3 times root 3. Root 3 times root 3, which is root 9. Square root of 9 is 3. So it's 6 times 3, right? Root 3 times root 3 is 3. 6 times 3 is 18. So this guy here, n, is 18. 18 is not more than 12 root 3, by the way. This is longer than that, so don't worry about that. All right, number 13 and 14 are 45, 45, 90 triangles here. Now you have a leg, 5. This y should also be equal. These are 1 to 1. Ratio relationship. One's 5, the other's 5. X is root 2 times larger, so it's 5 times root 2, which is 5 root 2. Okay. Number 14, same-ish. We have a leg. So here's the other leg, y. This is 10 root 2. It's a 45, 45, 90. Now you got to take, so x is going to be taking the 10 root 2 and multiplying that by root 2. Well, root 2 times root 2 is 2, and 10 times 2 is 20. So x equals 20. Excuse me. Yeah, I felt like they could have done more with those kinds of problems as far as trickery goes. Maybe we run into others, maybe not. All right, find the measure of the indicated angle to the nearest degree. Now we are back in trig scenario. This is a variable, a Greek letter known as theta. Treat it like an x. I'll use theta though. So in terms of theta here, in this right triangle, here's the leg adjacent, and here's the hypotenuse. I shall use cosine to set this thing up. If I take cosine of my angle, I get adjacent over hypotenuse, which is 12 over 13. The cosine of some angle gives me some decimal. That's the same thing as the decimal that 12 divided by 13 gives me. What is that? How do I find it? It's not trial and error. It's not guess and check. There's actually there's an inverse to cosine that we can use to get theta by itself, and it's called inverse cosine. And it looks like this. It almost looks like it says cosine to the negative first power. If I take the inverse cosine of this side and the inverse cosine of that side, what happens is these cancel. You're left with theta. Theta equals the inverse cosine of 12/13. Now, we have our calculator to tell us what that is. The calculator knows that in any similar right triangle that it has a 12 to 13 ratio relationship between the adjacent and hypotenuse, adjacent leg and hypotenuse, I can tell you what the angle measure is. Your calculator knows that information. I do not. So let's do the inverse cosine of 12/13. Generally, the inverse cosine button is above the cosine button, so I have it right there. I have to press the second there. So it's around 22.6 degrees. Oh, 23 degrees. It says round to the nearest degree. So it's around 23 degrees right there. I'm going to go ahead and give you that. And there it is. So it's best to do it that way. Get your setup based on what it is you're working on. Get the exact answer because that's what you got to put in the calculator anyway. And then compute. Number 16, I should use opposite, adjacent. I should use tangent here. The tangent of some angle. Remember, we take the tangent of the angle. The ratio is the result, 4/13. I will take the inverse tangent of both sides and get theta as the inverse tangent of 4/13. And I'll use, this time, my calculator to get it. I expect a value less than 45 degrees for sure. Probably maybe even less than 30, I have no idea. 17, less than 20, 17.7 degrees. It's about 18 degrees, 17.1 degrees. So it's about 17 degrees there. All right, 2 more. This, hopefully you should know what this one is because these are, this is an isosceles right triangle. That means it's going to be 45. If you're uncertain, let's go ahead and set that thing up and see what we get. Tangent again, right? Tangent of some angle is 3/3. You could also call that 1, right? Tangent of theta equals 1. Theta is the inverse tangent of 1. You can do 3/3 or 1, right? They're both the same thing. Try that in your calculator, see what you get. Inverse tangent of 1 If you're in degrees, you should get 45 degrees. Again, your calculator understands what kind of triangle it's in. It's dividing the opposite and adjacent. They become the same. They're the same value. So it says, hey, that's in 45. That's a 45 degree angle. That would do that. I couldn't tell you what this next one was, though. Going to use cosine, adjacent hypotenuse, right? Cosine of our angle is adjacent over hypotenuse. Theta is the inverse cosine of that value, 4.4 over 11. You know, it's not worth reducing the fraction if it's going to cause you a struggle. So, like, I know 3 over 3 is 1, and it's easier for me to type. But I'm not going to try and reduce this thing if it's just going to make me get a wrong answer. We're going to take the inverse cosine anyway, so we might as well, you know, let our calculator help us out. I'm getting 66.4, so I'm going to say around 66 degrees there. Okay. All right, find the missing side lengths. Leave your answers as radicals in simplest form, no decimals. So this is a right triangle where you know 2 side lengths. The third side length is, well, through Pythagorean theorem. If I don't know this x right here, I get to say 5 squared plus 2 squared equals x squared. 25 plus 4 is x squared. X squared is 29. If you take the square root of both sides, x is the square root of 29. I cannot simplify that radical. It is a prime number. It contains no perfect square factors. Now, I'll tell you right now on number 20, the answer is 6, and I'll tell you why after we do Pythagorean theorem. But let's do that. X squared plus 8 squared equals 10 squared. Notice 10 is the hypotenuse, so the third side, that c, is the one that we write on this side here. X squared plus 64 equals 100. X squared equals 36. Take the square root of both sides. You do indeed get x equals 6. Mr. Robinson, you cheated. You did this before. You know. Well, I may have, but I've done this before hundreds of times in math. What I just did here was this is a Pythagorean triple. This is the 3, 4, 5 Pythagorean triple right here. What am I talking about? In right triangles, 3 squared plus 4 squared was, 3 squared plus 4 squared equals 5 squared. And there are some other Pythagorean triples. Hey, there was one up above. I didn't call it out. This would have been a 5 right here. 5 squared plus 12 squared is 13 squared. There are some 3, 4, 5, 5, 12, 13. These are the only 4 I know off the top of my head. 8, 15, 17, and 7, 24, 25. These are the 4 smallest unique Pythagorean triples that exist out there, as in 3 squared plus 4 squared is 5 squared, 5 squared plus 12 squared is 13 squared, 8 squared plus 15 squared is 17 squared, and 7 squared plus 24 squared is 25 squared. Those are the 4 smallest ones. Pythagorean triples are ones where you have integer values of your side lengths, as opposed to, like, 2 squared plus 5 squared is root 29 squared. That was a different one, right? So those are Pythagorean triples. Now, you just saw one that had 6, 8, and 10 in it, and I just said that these are the smallest ones. No, I said those are the smallest unique ones. 6, 8, 10 corresponds to 3, 4, 5. 6 is double 3, 8 is double 4, 10 is double 5. Those are all double those lengths. 30, 40, 50 would have been a Pythagorean triple that falls under the similarity bit of the 3, 4, 5. So this still has to do with similar triangles. Anyway, my mind goes straight to, hey, can I reduce these values? Yes, if you divide it by 2, that's a 5. If you divide that by 2, that's a 4. And then this would be a 3. So if I double them back up, 3 times 2 is 6. Yeah, I did that in my head, but I also see the 6, 8, 10 quite often. And if I run into more, I'll tell you about them. All right, find the value of each variable. This is back to our special right triangles, the 45, 45, 90, and the 30, 60, 90. Now, we have to solve for x and y in a triangle where we know no side lengths. So we have to find a side length. In the 45, 45, 90, we know this side length is 9 root 3. That's a leg. This leg also would be 9 root 3. But what I need is this hypotenuse, because the hypotenuse of the 45, 45, 90 triangle is also the long leg of the 30, 60, 90 triangle. That length right there is 9 root 3 times root 2. Right? Root 2 times larger. So that's 9 root 6. So I'm going to place a 9 root 6 right there. So in my 30, 60, 90 triangle, oh, this is good. The 9 root 6 is opposite the 60. So opposite the 30 right here, I have to take the 9 root 6 and divide by root 3. Because remember, the 60 degree angle is root 3 times larger than that one. So I have to divide by root 3. And root 6 over root 3 is root 2. So x is 9 root 2. And what I'm going to do is take that 9 root 2 to find y, because I want to take the short leg opposite the 30. The hypotenuse is double that of the short leg. If you remember in the 30, 60, 90, it's a 1 to 2 to root 3 relationship there. 1 to 2 is double. What is 9 root 2 times 2? That is 18 root 2. 18 root 2. A lot of messy writing with me all around, but that's how it's working. I'm more than 2 hours into this thing, and I've only completed half of this stuff. That doesn't mean the other half isn't shorter. I have no idea. But I've only completed half of it. We'll see where we get. Proofs. These are ones with parallel lines cut by transversals. Here we go. Let's do our proofs. Given A, line A is parallel to line B. Let's mark that up with some arrows like that. These two are parallel here. Okay, that's given. Given that line C is parallel to line D, let's use that info to prove angle 6 is congruent to angle 10. Now, angle 6 is right here. Angle 10 is right here. I would love to call out corresponding angles. You know, corresponding angles are these angles right here, and when two parallel lines are cut by a transversal, then they're congruent to each other. So you almost look at these and you say, corresponding angles. Well, not quite, because they're not cut by a transversal. Angle 6 is formed by lines C and B. Angle 10 is formed by lines D and A and D, right there. They don't share a transversal. They don't share a line together. So what we can do, however, is use the parallel lines that we are given to come up with angles, maybe with 6 and 10, come up with angles that maybe are, say corresponding angles with them, and then make those congruent, and then because of that, we could then use some transitive property stuff. So like this. Let's relate angle 6 to an angle that 10 can also relate to. Do I want to make this easier or harder for you? You know what? What's the one below this? These have corresponding angles here. Let's do something else that's not corresponding angles. You know what? Let's relate 6 with 15. I'm going to relate 6 with 15 because 10 can also relate with 15. I'll show you where in a second. 6 and 15 are known as alternate interior angles. Here's my transversal B. Here's my transversal B. Here are these two parallel lines C and D, and these are on opposite sides of the transversal in between the parallel lines. Angle 6 is congruent to angle 15 because of what is known as the alternate interior angle theorem. And here's what it states. You have to be very, very careful with this. They are not congruent because they're alternate interior angles. They're congruent because alternate interior angles are congruent when lines are parallel. Line C is parallel to line D. We know that. That's given. Because line C is parallel to line D, and because these are alternate interior angles, that makes them congruent with each other. This statement could not have been made unless it was given or unless I knew this. And because I know this, I can do that. Now, cool. A being parallel to B can allow me to draw a connection between angle 10 and, hey, how about angle 15 as well? Angle 10 is also congruent to angle 15 because when those two lines are cut by that transversal, we have alternate exterior angles that are congruent to each other, AEA theorem, which says because these two parallel lines, I can make that so. Now, I went the harder way with this, meaning I could have made a connection with say 6 and 14 and 10 and 14 and called those corresponding angles and had it, just called it a day. But I think I'm going to be using that for the next problem that I do. So I'm just going to avoid that and just say, here's a good one. Here's a good one there. Okay, now, because these two angles are congruent to the same angle, that makes them congruent to each other, right? That makes sense. 6 is congruent to 15. 10 is congruent to 15. Well, 6 and 10 must be congruent to each other, therefore. And that is true. Angle 6 is now congruent to angle 10 because reasons. Because two angles congruent to the same angle are congruent to each other. That is known as the transitive property of congruence. The transitive property of congruence. One more time. Two angles congruent to the same angle are congruent to each other. Also true for segments. Two segments congruent to the same segment are congruent to each other. So it's because of this statement here and this statement here, statements 3 and 4, that I'm able to make statement 5. There's my proof. All right, next one. We are given line C is parallel to line D. It's very important that you mark this thing up. C is parallel to D. Also, angle 1 is congruent to angle 2. The exact angles that we couldn't find to be, that we had to prove to be congruent before, we are now shown to be congruent. Awesome. We got to prove that line A is parallel to line B. Okay. Let's associate angle 3 with angles 1 and 2. And it's very easy to choose which one because there's only one more that they give us. So let's associate angle 3 with these two. Notice how angle 3 is a corresponding angle pair with 1. And it's also a corresponding angle pair with 2. Does that mean that I can automatically call angle 3 congruent with angle 1, angle 3 congruent with angle 2? Yes to one of them, no to the other. Let's talk about it. We can say angle 3 is congruent to angle 1. I'll say 1 with 3. Angle 1 is congruent to angle 3. How come? Well, they are corresponding angles, and these lines are parallel. That is known as the corresponding angles postulate. If you say theorem, whatever. I think some teachers might say that. I say postulate. Postulate is the statement that we can assume, accept, and assume to be true. I already said that. Assume, accept, and believe to be true. But if lines are parallel, corresponding angles are congruent. That's the important part. Can I say angle 3 is congruent to angle 2? Oh, you know what? I can now. Now I can say angle 3 is congruent to angle 2. I can't say, so here we go. Angle 2 is congruent to angle 3. It is not because of the corresponding angles postulate. These may be corresponding angles. But the postulate states if those lines are parallel, if this line was parallel to this line, then corresponding angles would be congruent. Well, here's the thing. They're not only not known to be parallel, but it's what we're trying to prove. So you can't use that double whammy version. I always try and equate it to murder to my kiddos as far as like, you can't use murder as a reason to prove that something else is true and therefore they murdered them. No, you have to, we're proving those lines are parallel. So we can't say they're congruent because if the lines are, no. You have to find another reason to say they're congruent, and we have it. We just did it in the last one too, right? Two angles congruent to the same angle. 2 and 3 are both congruent to 1. So 2 and 3 are congruent to each other. That's, once again, the transitive property of equality. I'm talking too much on this stuff. Okay, now, these are corresponding angles, and we just found them to be congruent to each other. Well, you know what's true, too? That corresponding angles postulate is biconditional. The original postulate states if lines are parallel, then corresponding angles are congruent. The The converse of the statement says if corresponding angles are congruent, then those lines are parallel. Finally, line A is parallel to line B because those corresponding angles are congruent. Line A is parallel to line B by what's called the converse of the corresponding angles postulate. The converse of it. That's why. I'm done. Not with everything. Write the equation of the circle. Hey, we're back to a circle equation. In standard form with center 2, -3, and radius 4, then graph, show exact points. All right, it's nothing we haven't done before. Here's the equation of the circle. X minus h quantity squared plus y minus k quantity squared. Remember, minus and negative is plus. Equals r squared 16. So that's the equation. Let's also use the information for the graph. The center's at 2, -3 right there. A radius of 4 means let's go up 4, down 4, left 4, 1, 2, 3, 4, right 4. 1 fish, 2 fish, red fish, blue fish. Whoa. Whoa, fish. Oh, fish. Here we go, fish. Circle tool. Whip that out of your back pocket. You know what? You guys can have a compass, I suppose. It's possible. Oh, the equation is supposed to be written in here. That's okay. I got you. All right. There it is. Yeah, I don't really have anything else to write on that. Write the equation of the circle in standard form, show all steps. So this is one where, once again, we got to get in this kind of form here. So we have to do the completing the square business that we did before. Okay, this is where we start to get a mix of different kinds of problems. We are, well, I guess we're still on review 4 here, part 4. But, you know, a different review mixes back to some of the things you saw before. That's one reason why this might go a little faster, because we might recall some things that we've previously done. Okay, I'm going to take the x terms together, x squared minus 10x, and complete the square here. Then I'm going to take my y terms, y squared plus 6y, and complete the square here. And let's subtract the 30 over and add whatever we just ended up adding on this side. With a 1x squared, I can take my negative 10, divide it by 2 to get negative 5, and square it to get positive 25. Let's add 25 to this side. With my 1y squared, I can take my 6 and divide it by 2 to get 3, and square that to get 9, and I'll add 9 over here. This factors down to x minus 5 quantity squared. This factors down to y plus 3 quantity squared. And this adds and combines to make 4. There you go. I'm reading everything. They're not asking for anything else, including center, which is at 5, negative 3, and radius, which is 2. A mission control observer 8 kilometers from the launch pad observes a space shuttle ascending. The angle of elevation from the observer to the shuttle is 43 degrees. How far is the shuttle to the nearest tenth from the observer? All right, it's a very trig-based question. It's a word problem here. Now, there are some assumptions we have to make. They kind of help us out with one of them. When something's ascending, they're saying straight up. Okay, so we have a mission control observer 8 kilometers from a launch pad. I'm drawing some ground level. I'm drawing myself a little launch pad here. 10, 9, 8. And we have a mission control observer right here. He's 8 kilometers away from the launch pad. Okay? There's a space shuttle that's ascending from the launch pad right here. There it goes. Whee! The mission control observer is watching the space shuttle. With binoculars or whatever the heck he's looking at him with, he's looking upward from a horizontal line of sight of 43 degrees. We want to know how far the observer is from the space shuttle. Now, the other thing I'm missing here is that since this is going straight up and ground is horizontal, this is a right angle being made here. So we have a right triangle. We have basically, without all the fancy pants stuff, we have a right triangle with 43 degrees, not drawn to scale, 8 kilometers, and x. And we got to solve for x. That's what's happening. So, how do we solve? Trig. We have a 43 degree angle. We have the angle adjacent, and we need to find the hypotenuse. That is cosine. The cosine of 43 equals 8 over x. Multiply both sides by x. Divide both sides by cosine of 43. X equals 8 over cosine of 43. Remember, we should get a number that's more than 8. This is the hypotenuse, right? Oops. It should be close to root 2 times larger than 8. It'll be close to 112. It'll probably be around 110 or something like that. 8 over, divided by cosine of 43. I'm sorry, 110. 10 point something. I don't know what I'm saying now. 10.9, close to 11. Why did I say 110? I was thinking of 80 instead of 8. I'm sorry. I shouldn't have even said anything. Around, what did it say? To the nearest tenth? So 10.9 kilometers. 10.9 kilometers right there. Okay. Oh, I know why I said it. Square root of 2. I'm trying to defend myself. Square root of 2 is around 1.4. So to do 8 times 1.4, I was trying to do 8 times 14. That's why. All right, 10.9 kilometers. And that's it. All right, for numbers 5 through 7, given ABC is a right triangle with measure of angle C is 90 degrees. If the tangent of one of the complementary angles is given below, find the tangent of the other acute angle. Draw each triangle. All right, let's draw these. I know I'm in the way for the last one. But they said C is the right angle. So let's say we got AB there, ABC, ABC, and right angle, right angle. Okay. Tangent of A is 0.25. So kind of a couple ways we can look at this. The way I mostly want to look at it is the ratio itself. 0.25 is 0.25 over 1. So you could say the tangent of A is opposite over adjacent like this. So then they're saying find the tangent of the other acute angle. So like we got to find tangent of B. So tangent of B would be 1 over 0.25. And we would you could use a calculator to find that. I can tell you right now it's going to be 4. One other version you could do of that, obviously 0.25 is 1/4. Remember, all these triangles are similar to each other. The angle of A won't change by growing these 4 times larger. I could call that 1 over 4 straight up. So tangent of B, once again, is 4 over 1. That gives you 4. Sorry for speaking too fast on any of that. The whole idea of this is that you've got to have some number sense and know your math on that to do it. But yeah, that's what's happening. So essentially what's happening for all these is you reciprocate what's here. If tangent of A is this over that, tangent of B is that over this. You flip them. By flipping them, you're taking the reciprocal. Tangent of A is 1 divided by that. Tangent of A is 1 divided by that. Those will be your answers. But if we're trying to get an exact answer, I think using the fraction is probably most appropriate. So here I can call that 3/4 here. Here I can call this 1/2. And when we do tangent of B as 3/4, 3/4, then tangent of A, hold on. Tangent of A would be 4/3. And if this tangent of B is 1/2, whoops, then tangent of A is 2/1, which is 2. I mean, those are the exact answers. That's how you flip it. An alternative to these methods, it would take some more time. You'd have to use your calculator, and you'd have to rely on the calculator for what you do. Let me show you just one example, like the first one. If tangent of A is 0.25, then that means A is the inverse tangent of 0.25. I'm talking about the angle. You can actually find the angle by doing inverse tangent. Let me tell you what it is about, just right here. Inverse tangent of 0.25. It's around 14 degrees. Around 14 degrees. It's like 14.03. Well, I should have used my other calculator, I guess. But there's inverse tangent of 0.25. Okay. B's angle is the complement of A, right? They told you they're complementary. B is 90 minus 14, or that number. So let me do that. 90 minus the previous value. It's around 76 degrees. It's 75.9637563. And now we can take the tangent of B. So I can do the tangent of my angle here. Tangent of the previous answer. I want you to check this out. Tangent of that previous angle, that 76 degree-ish angle, although it's rounded, it's 4. It's 4. So you can kind of work it that way as well, knowing that they're complementary in that kind of way, and find the angle, take the tangent of it. But you got to do the exact one, and it takes a few more steps. In this one, well, then your calculator is going to say 1.3 repeating. I'd rather give an exact answer. 4/3, an exact fraction. All right, let's move on forward. Got a word problem. Looks like Trig may be involved because of the 32-degree thing. Brent is planning to fence his backyard. Every side of the yard except for the side along the house is to be fenced. If the fencing costs $4.75 per yard, how much will the fencing cost? Show all work, label units. Well, here's his house. No fencing on the house itself, I suppose. Here, yeah, fence is backyard. So here's the yard right here. We're going to build fence along anything that's blue. So to find out how much it costs, you got to find out how many yards you need of fencing. We have the 13 here. We have the 23 here. We just need this length right here, this KL. I'll just call it an X. And we can use trig for that because we have a 32-degree angle measure right there, and we have a right triangle right here. What we need is another length inside here. Now, this is a rectangle. That means I don't know what these lengths are specifically, but I do know if this is 13, then so is this. And if that's 13 and the whole thing's 23, that makes this part 10. So in this right triangle here, I know that opposite the 32 is the 10, and I need the x. So I can use sine for that. The sine of 32 degrees is 10 over x. You've probably seen this switch place thing quite a bit here now. X is 10 divided by the sine of 32. That's an exact value. And I may be using the exact value in my calculator when it comes to yardage. They're celebrating behind me here. I may use the exact answer of the calculator, but I will round it for you here. 10 divided by sine of 32. Oops, that's 10 times the sine of 32. I would have recognized that would have been the wrong answer because it should be more than 10. So it's around 18.87. I'll just put 18.9 yards right there. So it's around 18.9. So the fencing altogether adds all that stuff up. Take that perimeter. 13 plus 18.9. Remember, I have the exact calculator value. Plus 23. So 13 plus that answer plus 23 is around 54.9 yards. Okay, I have 54.9 yards of fencing. Every yard of fencing costs $4.75. How do you find the overall cost? I know a lot of people know that general form of math there, and you say you multiply them, and you would be totally right, and that is totally what you do. If you don't know, and if I can equate it to the things we've talked about before, this is all about proportionality. If every 1 yard costs $4.75, then 54.9 yards costs this much money. I'll use Y this time. cost this much money in dollars, right? It's a proportion. Cross multiply, you get y equals 54.9 times 4.75. Yes, you do multiply, but it's through that proportionality that you can understand why you multiply by that. Anyway, I still have my exact number, my 54.8-ish number right here. I don't know if it'll focus, but I have my 54.8-ish number right there, okay? I'm going to multiply that by 4.75. Now I'm getting 260.636. So dollars 260.64. I'm going to round up. Got to give them that extra penny to be sure. Come on, Brent. It's a cheap fence in and of itself already. You got this. You got this. Okay. We got some circles and some circles and some circles. Find the value of x, show all work. I probably want to go fast through these because I taught this most recently. So it's most recent for my students, and it's probably most recent for you in terms of video watching for integrated math 2 stuff. So two lines, two chords intersecting inside of a circle here, and we're trying to find an angle measure inside there. We have some arcs that are measured right here, which means, if I label this y right here, there's a better relationship between y and the 70 and 360. Y is half of the sum of 70 and 160. If I said 360, I meant 160. So y is half of 230. Y is 115 degrees. Now we need x. X and y are a linear pair here. X is 180 minus 115. X is 65 degrees. Boom, I'm done. Now there's another version of this without using any y whatsoever, but then it will involve kind of understanding what these two bits add to. Because x is half. X is, if I called this a and called this b, I guess now you're using different letters, but I'm not really going to. X is half of the a plus b, that angle. That's the formula that we're doing. It's half the sum of those, right? Now, I don't care what a and b are independently. I care what they are collectively, because when I'm going to add them. Now, what are they? Well, 70 plus 160 was 230, right? Together, these are 230. These are the rest of what makes 360, because the whole circle has a 360. 360 minus 230 is 130, so it's half of 130. Which gives you 65. So they add to 130 collectively. I don't know what they are separately, but collectively they're 130 degrees. There's another version. Okay, number 10. Number 10, we're solving for x. X is an inscribed angle. That's an angle that's on the circle. Its endpoints go over here, and we see an intercepted arc right here. X is half the measure of its intercepted arc. Whatever this measure is, divided by 2, we'll get x. Well, what is that? Half of what? Here you see the center of your circle, and you see that ray cutting through there like a diameter. That makes this entire thing right here a semicircle. A semicircle measures 180 degrees. You have 110 degrees on this portion of the arc. That makes this portion 70 degrees. 110 plus 70 is 180. X, as an inscribed angle, is half of that 70. X is 35. Make sense? Now, this relationship here, and it looks like we do it also for number 13, sort of-ish. We got to solve for this angle intersecting outside of the circle from a secant line and tangent line. Now, when lines intersected inside the circle, your angle was half the sum of two arcs that are the opposite, whatever thing. This angle right here is half the difference of two arcs here, of this minus this. It's the intercepted arcs that are formed that are captured by the lines from your arc. So notice how the lines go out here and here. It's that arc and that arc right there. So we know that one of the arcs is 60 degrees, something minus 60. We got to find out what this is right here by knowing all this plus this plus this, all of them make your 360 degree, circle. So this guy is 360 minus 130 plus 60. I believe that to be 170. So this is 170 degrees right here. So x is half of 170 minus 60. For the sake of time and everything, guys, I'm not getting deep into the why this is. I do believe I have videos that state it. But it's going to be 55. Whoops, let me put x there. X is about 55 right there, or exactly 55. There. But yes, intersecting outside the circle. So the way I state it, hopefully, is a way that you can make sense of it. And same thing with all these other ones. Maybe that's why these will go a little faster. Number 12. Now we're not talking about the angles, but we're talking about lengths. When two chords intersect inside of a circle, the two segments broken up by the chord multiplied together, x times 3, will equal the same thing as 4 times 6. It has to do with similar triangles. I'm not going to get too deep into it right now, but x times 3 equals 4 times 6. 3x is 24, x equals 8. If every problem was that fast, like the proofs. Once again, this is an angle intersecting outside the circle. Doesn't matter if they were secant lines, tangent lines, or what have you. This angle, 40, is half of the difference of 96 and x. 40 is half of 96 minus x. Now maybe, just maybe, you do not want to distribute the 1/2 into the 96 and negative x. I don't want to either. If 40 is half of this difference, then this difference is double that of 40. Meaning I can double 40 and that'll equal the difference there, right? Basically, I took this equation and multiplied both sides by 2. See how that goes away? See how I don't distribute the 2 into those? So 80 equals 96 minus x. I mean, some people could tell me 96 minus what is 80? But if I add x to both sides, subtract 80 from both sides, you get x equals 16. Right there. So 16 degrees is what goes there. Double check it. 96 minus 16 is 80. Half of 80 is 40. Okay, it works. Now, number 14, actually 14, 15, and 16 all will fall under this same thing that I'm going to do each time with these. Whenever you have secant lines and or tangent lines intersecting outside of the circle, their lengths have another proportional relationship. It has to do with similar triangles. I've brought it up in previous videos that work as follows in terms of a formula. Outside times whole equals outside times whole. I'm referring to the lengths. The length of the outside of this segment, 5, times the whole, 5 plus 7, equals the length of the outside here, x, times the whole, which is x plus 4. 5 times 12 is 60. X times x plus 4 distributed is x squared plus 4x. Well, this is a quadratic equation. We've dealt with a couple before. Let's do this. These are often factorable, so let's try that. Subtract 60 from both sides. Set it equal to 0. You factor this. You find two numbers that multiply to make negative 60 and add to make 4. Those are 10 and negative 6. If x plus 10 equals 0, then x equals negative 10. If x minus 6 equals 0, then x equals 6. If I substitute 6 into here, all's good. I have a positive length. If I substitute negative 10 into here, that's all bad. I have a negative length. You cannot have negative or 0 lengths. Negative 10 is extraneous. Negative 10 does not work. X equals 6, however, does. That is the answer and the only answer. Okay, number 15, same thing. We're going to work outside times whole equals outside times whole. I have outside 5 times whole, 5 plus x. Or x plus 5, how about that? Outside times whole equals, not inside, but outside 6 times whole, 9 plus 6, that's 15. This is not a quadratic, as I distribute here. 5x plus 25 equals 90, I think. 5x equals 65, x equals 13. It's algebra the rest of the way. I'm setting it up geometrically for you, though. All right, this is another outside times whole equals outside times whole. 5 times 5 plus x, or let me write x plus 5 again. That looks a little cleaner. 5 times x plus 5 equals. Now here, the 7, the outside is the same thing as the whole. 7 times 7, right? 7 squared. So 5x plus 25 equals 49. Oh, 5x equals 24 and x equals 24/5. That's as reduced as you can get. I know some other people might want to hear the other thing, and that should be 4.8, I think. Hope I'm not wrong. 4.8 or 24/5. That's the exact value that you're going to have to get there. Apparently, 5 times 9.8 equals 49. Is that true? Yeah? Yeah, that works. 4.8 or 24/5. That works out. Done with circles? Yep. Oh, back to geometry. Okay, so, well, it's all geometry. Back to proofs. All right, part 5. 2.5 hours in. We'll see where we get to time-wise in the end. You guys already know. You're in the future. Here we're going to prove triangles are just congruent. No CP, CTC needed. Apparently only 4 steps needed. They are asking to draw the triangle separately. I can probably mention why in a moment, but let's work the givens. We got TQS right here, congruent to RSQ, that is given. Angle, excuse me, TQS congruent to angle RSQ, that's given. We also have angle QRS. Well, I'll tell you what. Oh, yeah. No, yeah, this will be 4 steps. Angle QRS is congruent to angle STQ. Where's that? QRS up here is congruent to STQ. That's given. Okay, the reason they might ask you to separate the triangles is because you can see this overlap here. Now, there's a reason the triangles are together, and that's actually going to help us solve this thing. So the togetherness is beneficial. But what I will do, I'll show you a different version, but I want to color code these at least to extend that. We have these 2 triangles we want to prove to be congruent. This triangle, congruent with this triangle here. And the reason I point these out is because based on the givens that you already see, you can tell that those are angles that are marked up. I got this angle and this triangle in the blue, and in the green I have this angle and this angle. So you can kind of see that separation. I'd have to actually group them to separate them. That sounds weird. I have to group these. No, I hate when it does that. There we go. There's that triangle, that RQS, and then this one right here, right? So separated, you can see, all right, that stuff. So we know, again, this is congruent to that, and we know this is congruent to that. Now, the part that when they're separate you can't do is something that you can do when they're together is this QS is a shared side in both triangles. I can mark this thing as if it's congruent to itself. This is congruent to this. See, separated, you have no way of knowing they're congruent. Together, it is a shared side. I can say QS in one triangle is congruent to, I want to call it SQ in the other triangle because of how it kind of flips over to make it so, how they correspond. This is the reflexive property of congruence. It is a shared side in both triangles. The shared side, and they're congruent. It's congruent to itself. So having them separated also helps me kind of maybe come up with the triangle statement. Well, you know what? We have the triangle statement. Triangle TQS is congruent to triangle RSQ. But do you agree with that? TQS RSQ. That's TQS RSQ. Yeah, I agree with that. Now, what's the reason? This is another reason having them separated helps. It's an angle, angle, side. Angle, angle, side. We got angle, angle, side, triangle, congruence theorem. Okay. State why triangles are congruent. If they are, state the congruency statement of which triangles are congruent. These go pretty fast here. Find the markings of parts that should correspond here. Congruent, congruent, congruent. That's a side, side, side case. Now they give you triangle ABC is congruent to what? Notice when you do ABC, you go across the 1 tick mark to the 3 tick mark. We got to go across the 1 to the 3 and say QRP. Triangle QRP. Letter order matters. Correspond the parts. There it is. Next one, triangle ABC here. We got a side angle side case with corresponding side angle side. This is side angle side. Which triangles are congruent? When they say ABC, notice they go to the unmarked across the one arc, one mark to the one arc. Let's go no marked, one arc, one mark, one arc, X, Y, Z. That is alphabetical. Was the other one alphabetical? No. By side angle side. These ones right here, this unfortunately, I see it right now, and unless I can pull out more information, which I can't, this is an angle side side case. Angle side side is not a reason to show triangles are congruent. Now, I can't say, so don't make a statement to say what corresponds. We can assume what should correspond based on what we see, but we don't know they're congruent, so we don't want to make a congruence statement. Furthermore, we don't know they're not congruent either. We just don't have enough information. And I don't know what they want us to say if they're not. They say state why if they are, state the congruence that they are. It's not that they're not congruent, but there's not enough info. There are some versions where we would know they're not congruent. Can't come up with one really right now. But there's not enough information to say for sure that they are congruent. This is an angle side side case. It's not one of our triangle congruent statements. Last one, number 4. It looks like an angle side side case on number 4. The difference is these are right angles. And in a right triangle, if the hypotenuses are congruent and a set of legs are congruent, then the triangles are congruent by hypotenuse leg. It is the exception to your angle side case, because you can use Pythagorean theorem to show these are congruent, therefore you have side and side angle side and other things. But we cut it short and we say HL, it does. So what is it when we say ABC? That would be, A is the right angle, X, Y, Z, also alphabetical, by HL. Okay, more triangle congruence, let's see. Yeah, 5 and 6, same stuff. Now these ones here is a little different. All I have in these right now is side. Side on its own wouldn't be enough. But by the nature of the drawing, we can come up with more information, such as these two vertical angles right here. This is congruent to that. Now, I don't have to document and mark it up as a whole proof. I'm just marking it. So right here, well, I do have to mark it. I don't have to document it. That would be a side angle side case if so. These would be side angle side to say that ABC is congruent to, let's see, we go to the unmarked to the double mark. Unmarked, double mark, EDC. EDC. It's like a rotation, not a reflection. By side angle side. And right here we only have two sets of angles congruent, which ordinarily wouldn't be enough. Even three angles wouldn't. But you have a shared side in between, this BC and CB bit here. And they say triangle ABC. Notice the double to the single to unmarked. Double to single to unmarked, ZCB by angle side. And angle side's allowed, angle side is not. So based off that information, we could get those. All right, graph each circle. So they just say graph. They don't say write the equations. They do below though. So graph each circle, -4, 0, a radius of 4. Got a lot of circle things. For a multiple choice final where you don't actually have to graph them, this is quite a lot of work for us to do for these, I do believe. So there's that circle. Let's go ahead and write the equation since we're already here. This is your H, K, and R. So this is X plus 4 quantity squared plus, Y minus 0 is just the same thing as Y. So squaring Y minus 0 is the same thing as just squaring Y. And 4 squared is 16. There's the equation. Let me move myself to do number 8. And therefore 10. My back is not bothering me too much, but every time I think my pauses allow me to get up just enough, and hopefully I can sit more. Problem is I haven't been able to run or anything, so I just want to not injure it more. 4, -5 is my center. My radius is 3, so up, right, down, left. I haven't been able to run in 2 weeks, more than 2 weeks now. Been kind of a problem. It's probably going to take me away from wanting to run later. I'm like demotivated now. And sitting actually injures it more. X minus 4 squared plus Y plus 5 quantity squared equals 9. I'm not even done with my first video, much less the other videos I'm going to have to make today. That's just crazy to think about. All right, write an equation of each parabola in standard form with the given characteristics. So with these right here, you need a couple bits, and I think sometimes I'm not going to draw it. I'm not going to draw a huge graph, but I'm going to draw the idea of what these things are here. If your vertex is at 0, 0, and your focus is at 0, -1/2, vertex focus, the graph has to go downward because it goes inside the focus there. And the distance between vertex and focus is actually 1/2 itself. That's P. Actually, literally -1/2. But if you know what goes upside down, then you know your A value is going to be negative. But here are the important aspects of this. In the vertex form for an equation is either y equals A times x minus h squared plus k, or x equals A times y minus k squared plus h. Now, this is a y equals x squared equation because it's an up-down graph, right? So this is going to be in this format. We know h and k. We need to find A. Well, you learned before that P equaled 1/4A. It also just happens to be that A equals 1/4P. So if P is -1/2, then here A is 1/4 times -1/2, which is 1/2, -1/2. So your A is -1/2, your vertex is 0, 0. Wherever I can squeeze this right here is y equals -1/2 x squared. That's it. All right, number 12. Focus is 1, 5. Directrix is x equals -2. So your focus, 1, 5 up here. Directrix, x equals -2 is over here. Your vertex is right in the middle of your focus and your directrix. And again, the focus is inside the parabola itself, so it's going to go this way. So we know this is an x equals y squared equation. We can also find out what the vertex is because it should be halfway between, right? If this is P and this is P, it's going to be halfway between your focus and directrix values. If the distance between your focus and your directrix seems to be 3, because this is 1 and then -1, -2, so 1, 2, 3, then your p-value is 3 over 2, 1.5. So that can allow us to get not only the a value, but also your vertex. Your vertex is 1.5 away from either the focus or directrix. So so your vertex, the y value of the vertex is 5. We already know that. It's just going to be the same height as the focus point. But this part right here, you got to take, say, 1 and subtract 3/2 from it. And that's -1/2. So your vertex is at -1/2 comma 5. I'm just making sure I did that right. Yep. -1/2 comma 5. And then your a value is 1 over 4p. So a is, let me scroll down here, 1 over 4 times 3/2, which is 1 over 6. Because that's 2 over 1. 2 times 3 is 6. So your equation as an x equals y squared equation, wherever I can fit this, is going to be x equals 1/6 times y minus k squared plus h, so -1/2 there. There's the equation. Nice and fun. All right, vertex is at 2, 5. Directrix is y equals 0. That's the x-axis. 2, 5 is right there. Directrix, way down here. Now your focus would be way up here, right? Focus. Your graph goes upward. It's a y equals x squared equation. It's a positive x squared equation. The distance from the directrix to your vertex is 5. That's your p-value. Same with the focus. That's going to be p equals 5, right? So we have the p-value. We're going to use that to find a, and we know the vertex for hk. So let's just find a. A is 1 over 4p. 1 over 4 times 5. Which is 1/20th. Obviously, I'm not drawing my graph to scale. That's part of what I was trying to talk about before. So your equation is y equals 1/20th times x minus h squared plus k, like that. Okay. And the last one, vertex is at -2. Well, I don't know. Maybe there are more. Vertex is at -2, 1. -2, 1. By the way, my students aren't doing these problems. Focus is at -2, 5. Once again, going upward. The distance between vertex and focus, distance between 1 and 5 is 4, so p equals 4. You know your hk. This is a y equals x squared equation. So a is 1 over 4 times p, which is 1/16. Clearly, number 12 was the hard problem. You probably gave up on me on that. And this is going to be y equals 1/16 times x minus, plus x plus 2, quantity squared, plus 1. Teaching it like I've taught it before. And you know what? I was doing this with my integrated math 3 kiddos, so there are recent videos on that, actually. Probably the most recent video. I don't know if I've done another video since. Okay, more circles, and this whole page is all circles here. Solve for x, assuming lines appearing tangent are tangent. Tangent means touching the circle at least once, like this one is tangent right here. This one's not because you can see distance made right here, such as x. All right, we learned outside times whole equals outside times whole. So 3 times 8, that's 3 plus 5, equals outside 4 times whole, 4 plus x. 24 equals 16 plus 4x. If you distribute, subtract 16 and you get 8, I think, and divide by 4, you get x equals 2. Yes, I will be working relatively fast. We already did problems like this, and algebra. Basic algebra is something I'm not going to spend time talking about. All right, outside times whole. Be careful. The 4 is part of the whole. Equals outside times whole. Like so. Before I distribute, I'd love to combine that stuff. X Negative 3 plus 4 is 1. So plus 1 equals 5 times, I probably should have done that first. X minus 1, I believe. Distribute there, we get 4x plus 4 equals 5x minus 5. Subtract 4x, you get x. Add 5, you get 9. So x equals 9. I'm not double checking, but I assume my math is good. Outside times whole equals outside times whole. 4 times 4 plus x equals 6 times 6. 6 squared is 36. Instead of distributing, this time let's divide both sides by 4. So 4 plus x equals 9. Subtract 4, you get x equals 5. Woohoo! So let's just see if that works. It does, but let's see. Outside times whole is 4 times 9. That's 36. 6 times 6 is 36. That works. Maybe you don't know why that thing works based on the similar triangle talk I tried to mention before. But it does. It does. All right, this is an outside and whole. These are broken up segment parts. X times 4 equals 5 times 8. So 4x equals 40. Divide by 4, you get x equals 10. I mean, these can go really fast if you want them to. And I do. 2 hours, 50 minutes. Oh boy. 4 more circle sets on this end here. Once again, this times this equals this times this. So 4x plus 2 times 8, let me put that on this side, equals 9 times 4x. Let's go ahead and distribute this time. 32x plus 16 equals 36x. Subtract 32x, you get 4x equals 16. Divide by 4, you get x equals 4. Okay? I'm just going to trust it. Hope I'm good enough on that. All right, an inscribed angle is half its intercepted arc, right? So 70 is half of half of 141x minus 1. Now maybe we don't prefer to see it that way. If 70 is half the intercepted arc, then the intercepted arc is double that of 70. So instead, multiply everything by 2, and you get 2 times 70 is 141x minus 1. So 140 equals 141x minus 1. Add 1 to both sides. Divide both sides by 141. You get x equals 1. That makes sense. 141 minus 1 is 140. Half of 140 is 70. Okay, this guy, this 50, is half the difference of this and that. Or if I double the 50, then I get the difference of this and that. So 2 times 50, or 100, equals 12x plus 8 minus 4x plus 4. Now, you might want to quantify these. You're not foiling, but you do want to make sure you know that you are distributing the negative into the 4x plus 4 here. Distributing it into that. 2 times 50 is 100, and this becomes 12x plus 8 minus 4x minus 4. So 100 equals 12x minus 4x is 8x. 8 minus 4 is 4. So what are we going to do? Subtract 4. Divide by 8. You get x equals 12. And lastly, on this circle set on these problems here, 60 is half of the sum of these two. 60 is half of this plus this. So if you double 60, then you get this plus this, right? These are double the 60. So 2 times 60 equals 55 plus 5x plus 15. 120 equals 5x plus 70. To subtract 70, you get 5x equals 50. Divide by 5, you get x equals 10. Okay, fun algebra to do with in there. If you know your properties, then you're pretty well off. Whew, okay, part 6, last one. What do we have? 2 triangle proofs, an algebra proof, simplifying some more radicals, which we've done, solve a couple quadratics, some same side interior, vertical, remote exterior, isosceles, vertical, complementary angle pair. Okay, I can probably get this done in the next less than a half hour. Just the proof sometimes takes some time. Given PC and HR bisect each other. Prove, oh my gosh, this is going to be a little bit, we probably have to use every step. All right, let's write some stuff out. PC and HR bisect each other. That's given. All right. When I see bisector, specifically since they bisect each other, I know straight up if this bisects this is divided into two congruent parts. If this bisects this, it's divided into two congruent parts. I draw it first, but I document it next. And I think I'm going to do this on the same step because I might need every little bit of this thing here. So I'm going to say that PE is congruent to CE, and I'm going to correspond them like that. And also HE is congruent to RE. This is the definition of segment bisector. Definition of segment bisector for both of them. They bisected each other. And we have a vertical angle pair right here. These angle E's, if you will. Angle HEP right here. Let's just do it in green as we're there. Angle HEP is congruent to angle, let's correspond, REC. Angle REC, that's your vertical angles theorem. Now we have a side angle side case for these two triangles to be congruent to each other. Once again, we're proving parts to be not congruent, but something else. I'm going to get into that. But we're, I guess I only need 6 steps now that I've converged these into one. But I'm going to do the triangle congruence statement here, HEP, and I think these parts already corresponded. So HEP and REC. This is a side angle side case right here, side angle side congruence. Okay. To prove these two lines are parallel, I'm going to have to prove that, or I'm going to have to show that one of these sets of corresponding angles are congruent. Now that I know the triangles are congruent, this will work, and I can use either or. I'm going to go ahead and use H congruent to R. If you notice, I got to use double arcs. If you notice here, H does correspond with R. They are both the first letters in the triangle congruence statement. So angle H is congruent to angle R. By CPCTC, the corresponding parts of the congruent triangles are congruent there. Now here's the thing, if you notice, HR is a transversal for this line and this line right here. I just showed these two angles here are congruent. If you really look at the blue, these are alternate interior angles. Remember how I said if corresponding angles are congruent, then their respective lines are parallel? Same for alternate interior angles. If alternate interior angles, then those lines are parallel. PH and CR. And those, they even wrote them as corresponding things. PH, segment PH is parallel to segment CR because of the converse of the alternate interior angle theorem. We flipped it on its head. If the angles are congruent, then the lines are therefore parallel. And that does work like so. And that is the final statement there. So I guess this could have been the third statement. We would have been able to work it out. Can I draw arrows for you guys? How about this? Because the bisecting statement, we made that. We did this on its own independently. These led to congruent angles, or congruent triangles. Congruent triangles led to congruent angles. Congruent angles led to parallel lines. Good flow, for sure. All right. Given angles BDA and BDC are right angles, and AB is congruent to BC, even though they didn't correspond that, prove these two angles are congruent. So let's go ahead and prove that these two triangles are congruent to each other. So angle BDA and angle BDC, at least those corresponded, are right angles. That's given. Now it looks like I'm going to go through the HL bit here. I'm going to end up showing this is congruent by reflexive properties. That's an HL bit. So I want to say that these are right triangles as well. Triangle BDA and triangle BDC are right triangles by definition because they contain, are right triangles by definition of right triangles. Okay. Because of that, we can now go to the HL bit. AB, I didn't mention this yet. AB is congruent to, I want to say CB. CB, that's given. Okay, now we go to the congruent segments here. Is that a B up top? Yep. So BD is congruent to itself. Segment BD is congruent to itself, and I'm corresponding that properly. BD corresponds to BD. That is the reflexive property of congruence there. My hand is hurting writing. Of congruence. I definitely need a break before doing some of my other videos if I do another one today, because I've been on 3 hours now. So now we have the two triangles now congruent here. We have enough to say these two triangles are congruent. I can use BDA and BDC again. And I do like to use BDA, BDC. I do like to say the D in the middle for the right angle. So triangle BDA is congruent to triangle BDC by HL. The hypotenuses and legs are congruent, and one set of legs are congruent in both triangles. HL, triangle congruence theorem. And therefore, ABD and CBD, ABD here is congruent to CBD by CPCTC. These are corresponding parts of these two congruent triangles. Notice they even say ABD 3, 1, 2 and CBD 3, 1, 3, 2. So angle ABD is congruent to angle CBD by CPCTC. Let me write that here. CPCTC. Okay. 6 steps. Don't need all 7 there. Okay. Moving on forward here. Algebra. Okay. Given this statement here, 1/5 times a plus 10 plus 1 equals -2. That is very much given. Different ways you can do this here. I'm not going to distribute this at all. I'm going to multiply everything by 5, but before that I'm going to subtract the 1 over. 1/5 times a plus 10 equals -3. That is the subtraction property of equality. And then I'm going to go and multiply both sides by 5. So I get a plus 10 equals -15. That is the multiplication property of equality. I think that's going to save me some time. And then I can subtract 10 from both sides. Then you get a equals -25. Once again, the subtraction property of equality. And I'm done. There's my algebraic proof. Okay. Simplify completely to simplified radical form. So I mentioned in the very beginning, after the first set of proofs that we did, how the negative inside a square root leads to an I. So this would turn into 5 times I root 48. But I can still simplify the root 48. 48 is 16 times 3. And I choose 16 because it's a perfect square. So root 16 times root 3 is 4 root 3. So that becomes 4I root 3. This is 5 times 4I root 3. 5 times 4 is 20. You get 20I root 3 here. 20I root 3. And I'm going to speak a little bit faster on this now. This is something that we've done before. This is not a problem we've done before. We've simplified, but we haven't added them together. Now, it's pretty straightforward. You combine anything that's alike, that shares common factors. But right here, 3 times square root of -8. That is 3 times, so there's an I, right? Root 8 is 2 root 2. Root 4 times root 2. So it's 3 times 2I root 2 plus, and I got a 2 times, remember there's an I here. Root 50 is root 25 times root 2. So 5 root 2. So 5I root 2. 3 times 2 is 6. So 6I root 2 plus 2 times 5 is 10. 10I root 2. Notice how both of these share an I root 2 multiple. This is almost like 6x plus 10x. I mean, it's in the same way. It's how many I root 2s are adding. We're adding 6 I root 2s here. 10 I root 2s here. Total, that's 16 I root 2s, kind of like 16x. So 6 I root 2 plus 10 I root 2 is 16 I root 2. And we can add them as long as they, are like terms, as long as they share the same thing. If this was an I root 3, no, they couldn't combine. You would just keep them separate. But they're both I root 2s, and we're good. All right, let's try it with this one here. 2 root 27. Notice these won't have i's in them. There's no negative square root here. Root 27 is 3 root 3 because it's root 9 times root 3. Root 48 we already know is 4 root 3, right? We did that before. So 2 times 4 root 3. And then root 32 is root 16 times root 2, so that's 4 root 2. 2 times 3 is 6. 2 times 4 is 8, and there's 4 root 2. So here's an example here. I can do 6 root 3 minus 8 root 3, and that'll give me -2 root 3. That's, that's how we combine those two things. 4 root 2 does not combine with those, however. It stays separated in such a way that, they're not like terms. They don't share a common multiple in that sort of way, so we'll leave them like that. Okay, let's do the ones on the bottom here. Simplify. Excuse me. 5i times the quantity here. We're going to distribute. That gives you 10I squared minus 20I. Now, any I squared that you get turn into a negative 1, right? We can have i's, we can't, not denominators, but we can't have I squareds. So 10 times negative 1 is negative 10. So that becomes negative 10 minus 20I. And you want it in that a plus bi form, a being negative 10, b being negative 20 in this case. A plus bi form is like that. It's a complex, it's known as a complex number with a real part and an imaginary part. Here we're going to FOIL. We've done that before. 2 times 3 is 6. 2 times negative 2i is negative 4i. Negative 6i times 3 is negative 18i. Negative 6i times negative 2i is positive 12i squared. Well, negative 4i minus 18i, let me make sure I did that right. Yep, negative 4i minus 18i is negative 22i, plus 12i squared is minus 12, because I squared is negative 1. 12 times negative 1 is negative 12. 6 minus 12 is negative 6, so we're going to get 6 minus negative 6 minus 22i. And lastly, this is one I know off the top of my head based off difference of two squares and a bunch of other things. Let's talk about difference of two squares first. If you want to FOIL, great. But a plus b times a minus b is a squared minus b squared. This is 4i squared minus 1 squared. So this is 16i squared minus 1, or negative 16 minus 1, or negative 17. I'm just going to say that. Great if you know, otherwise go and FOIL, see if you get the same answer. Mine's a solution guide video. There's my solution. You can tell, I want to finish this for all of us, baby. All right, here we go. Is this the last page? Last page! Past 3 hours, but last page. Solve each equation by completing the square. You can't tell me what to do, but I think I want to do that. Quadratic formula is an option. Factoring is an option if it's factorable. I'm going to go ahead and assume if they ask us to solve by completing the square, it's probably not factorable. So let's go ahead and try completing the square. In order to do so, you want to kick the 80 out of the way here. I do have a 1x squared. I have an even linear coefficient. That's good. I'm going to complete the square here by subtracting the 80 to the other side with the 4. And whatever I add to one side, I add to the other side. If I divide this by 2, I get negative 7. If I square it, I get 49. So I add 49 to the side as well. Definitely not factorable because I'm going to have a negative here, and you can't take the square root of a negative. But I can factor this now. This factors to x minus 7 quantity squared. And negative 84 plus 49 is 35, negative 35. So I'm going to take the square root of both sides right there. And I'm going to get x minus 7 equals plus or minus I root 35. And you cannot simplify. Oh, I'm not done. So x is 7 plus or minus I root 35. And I cannot simplify square root of 35. It may be a composite number. It may have 5 and 7 in it, for example, 5 times 7. But neither of those are perfect squares, and no perfect square factors there. So we're good. Now, I could use quadratic formula on that. If you do, just make sure you add the 4 over, and then, you have your formula. If you want to work it out, here it is. I'm going to leave it to you. But here's the thing. You got to make sure you simplify not only your radical, but also your fraction. You got to make sure you get this exact answer. And if you don't, I mean, if you have a multiple choice test, this is what you're looking for. No other version's probably going to be there for you, but that is the formula where you can work it out. Keep in mind that this part's called the discriminant. I don't know if there are going to be questions asking you to evaluate the discriminant, but that's a portion of it. All right, number 8. Last quadratic equation to do to complete the square here, which I'll gladly do. Once again, I have a 1x squared. I have an even linear coefficient. So if I subtract the 30 over, I can add something to both sides here. 22 divided by 2 is 11. Square that, you get 121. So 121 there as well. These themselves are perfect squares. But when you combine them through subtraction or addition, I don't know if they do become perfect squares anymore. This is x plus 11 quantity squared right here. 121 minus 25 is 96, I think, so not a perfect square. But I will take the square root regardless, and I can simplify 96. It's not an imaginary solution set either. X plus 11 equals plus or minus. So I know a 16 can go into it, and I think that's the largest. It's 16 times 6. So root 16 times root 6 is 4 root 6. Subtract 11, you get x equals negative 11 plus or minus 4 root 6. Let's triple check I added everything right. That's correct. 21 and 6 and 96. Yeah. Looks good. Okay. Quadratic formula. If you go for it, you should get the same answer. That's what you're working toward. All right. Find the value of x. Do they look congruent? So if the lines are parallel, same side interior angles are supplementary, not congruent. So you add them. 2x plus 43 plus 2x minus 3 and set it equal to 180. Combine like terms, you get 4x plus 40 equals 180. You get 4x. Did we have this? It might not have been this problem, but did we have this math before? 4x equals, sorry, 140. And x equals, is that 35? Did we have that math before? I feel like we did for a different problem. That's okay. Number 10. Now, we didn't have this same problem, but we've had a very similar setup. Remember, this line does nothing for this angle and this angle. These themselves are vertical angles, angles opposite each other from, those vertical lines, angles opposite each other from intersecting lines. They're congruent to each other. 63 equals 5x minus 17. Add 17, you get 80. 5x equals 80. Divide by 5, you get x equals 16. So x equals 16 there. 4 more problems. Here we go. Isosceles triangles. We're back at them. If you look, we're trying to solve for x within this isosceles triangle where we know no such angles other than an angle is complementary to another angle in this triangle. This base angle is complementary with the vertex angle in this isosceles triangle. Let's start with this triangle right here. We got a 71 here. We got a 71 here. 71 plus 71 is 142. 180 minus, because these add to 180. 180 minus 142 is 38. So this is 38 degrees right here. If this is 38, 38 plus something is 90. 90 minus 38 is 52. So this guy's 52 right here. And in this isosceles triangle, base angles are congruent. If this is 52, x is 52 degrees. You don't need the vertex angle, and you don't need to add anything to 180 right there. Number 12, we have a remote exterior angle theorem in play. We know that these two interior angles add up to become the remote exterior angle. So 4x plus 2 plus 2x minus 9 equals 5x plus 3. 4x plus 2x is 6x. 2 minus 9 is negative 7. Subtract 5x, add 7. You get x equals 10. Notice how I don't want to do all the proof. Addition property of equality and combine like terms. You can work things out a lot better with the algebra. 2 more. We have another set of complementary angles here because they add to make the right angle. So this plus this adds to 90 degrees. Right? Not supplementary, not congruent, but complementary. Not really a bigger part of our jargon recently. Just recently right here, yes. But normally we talk about congruent or supplementary. And I get it. But you still got to know things can add to 90. X plus 3x is 4x. 12 plus 2 is 14. Subtract 14 from both sides, and you get 76, I believe. And there is x equals 19. X equals 19 here. Let's see if that works. 19 plus 12 is 31. 3 times 19 is 57 plus 2 is 59. 31 plus 59 is 90. Yes, x equals 19. And the last problem, we have 2 intersecting lines and we have an adjacent set here. This is a linear pair. They are supplementary. 3x minus 17. They left us with an easy problem at the end. They add to 180 here. 64 minus 17 is 47. 3x plus 47 equals 180. Subtract 47, you get 3x is 133. Divide by 3. I don't think that divides by 3 very fairly. So it's 133 over 3. I'm going to leave it like that because it can't reduce. If you want the approximate or the mixed number version or whatever, it's 44 and a third, I think. 44.3 repeating, I think it is there. Okay, hey, so besides the fact that, listen, we didn't do exponential functions. If that's a part of what you're doing in your stuff and simplifying radicals and such, we didn't do any of those here, and I understand. We didn't do exponential functions. In our similar triangles, we didn't prove similarity via angle, side, or side, angle, side. We didn't do any of these through proportionality. We did triangle proofs, though, and I think a lot of those work things out. And we did proportionality, so make sure you test those with corresponding parts. And we did not do sector areas of sectors, like how much is the area of the shaded region here, and arc lengths, like what is that length right there with the measures with the smiley face there. We didn't do any of those here. If you refer to some recent videos where I talk about those, I think you can check those out. Similar triangles, I think you have to fall a little more to the wayside. Trying to think of what else might not have been covered. I mean, there might have been specific question types that we didn't really look into. Like, we didn't see when there were just two. Look, we didn't see tangent lines right here to talk about. It's still, this angle is still half of this minus this, but also these lengths are equal to each other. We didn't talk about the fact that radii intersect with these things at right angles, with the tangent lines at right angles, and therefore, because of this quadrilateral nature, that these two angles, the circumscribed angle and the associated central angle, are supplementary. We didn't talk about inscribed quadrilaterals being supplementary. You know what we didn't talk about? I might have to do this with my students. Hold on. X, Y. So x plus y equals 180. You know what else wasn't covered? We didn't talk about circumcenters and incenters. We didn't talk about perpendicular bisector theorem. I'm not going to do problems with them. I'm just covering some things you want to look at videos with. We didn't look at circumcenter, incenter. The circumcenter is the center of a circle from a I don't know if I can do this right. Da, 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 da. Wait, is this considered circumscribed or inscribed? Suddenly I forget. This is considered inscribed. So I'm sorry, an incenter. So an incenter would be the center of this circle from an, I guess the center's right here. Center from an inscribed triangle right here. That's the center. And what that means is that all three of these distances here, here, and here are congruent to each other. We didn't get into that. We didn't talk about the circumcenter, which would be a center inside. I was going to do this one first, and I grew it. We talk about the circumcenter right here, which means all these three distances inside this center are congruent to each other there, there, and there, and they're perpendicular, and all that stuff. So we didn't dive into those. Was that the only thing that I said? Oh, perpendicular bisector theorem, which states that if a point is on the perpendicular bisector of some segment, so if you have a perpendicular bisector right here, then these two, like if this point's on the perpendicular bisector, then it's equidistant to those parts right there. I guess that portion was really covered in that unit, so I got a C for my own students for my test if we're doing those. But guys, I'm out of it, man. That ought to do it for this one here. I know that wasn't part of the review. It's just something that, you know what? Some things get covered and some things don't. And they had 6 reviews where they didn't seem to ask questions there. That'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching. Take care. And if you are in Integrated Math 1 or 3, expect to see some videos coming up within the next 48 hours or so for you. I will see you in whatever next one. If this is the final time I see you for this year, guys. Hope you enjoy the year with me. And see you maybe in the next year, depending on what other videos I may make. Take care.